The next point is synchronous machines are basically used for the detection of the positional errors in an AC servo system, whereas a single phase AC supply is applied to the synchro transmitter. So synchronous machines are basically it is used for the detection of the positional errors in the case of AC servo system, and a single phase AC supply is basically is applied to the synchro transmitter. So we can say synchro machines are used for the detection of the positional errors in the case of AC servo system, and a single phase AC supply is applied to this synchro transmitter. So we can say the synchronous machines are basically used for the detection of the positional errors in the case of AC servo system, and a single phase AC supply is applied to the synchro transmitter. So we can say that the synchro machines are used for detection of the positional errors in the AC servo system, whereas a single phase AC supply is applied to the synchro transmitter. So finally, I can say that synchro machines are used for detection of the positional errors in the case of AC servo system, whereas a single phase AC supply is applied to the synchro transmitter. The next point is a phase lead network provides a positive phase angle over the frequency range of interest. A phase lead network provides a positive phase angle over the frequency range of interest. So I already told you, phase lead composite is always going to improve the transient response, whereas it is going to degrade the distressed response to a small amount of extent. So the phase lead means the output is always going to lead the input in some amount of angle. So therefore we can say the phase lead network is going to provide a positive phase angle over the frequency range of interest. So similarly we can say that the phase lag network is going to provide a negative phase angle over the frequency range of interest, because in the case of phase lag compensator, it is going to improve the steady state response. So it is going to degrade the transient response to a smaller amount of extent. So it is going to provide a negative phase lag because the output is always going to lag the input. So it is going to provide a negative phase angle over the frequency of interest. So this point always you have to keep in your mind. So therefore we can say a phase lead network is going to provide a positive phase angle over the frequency range of interest, whereas a phase lag network is going to provide a negative phase angle over the frequency range of interest. The next point is armature controlled DC servo motor is inherently a closed loop system. Armature controlled DC servo motor is inherently a closed loop system, as I've already told you in the case of DC servo motor, with the help of armature control as well as with the help of field control. As I've already shown in the figure block diagram, which is armature control DC servo motor will have a closed loop system, but there is a feedback. But for field control DC servo motor, there will be no feedback. It is an open loop system. So this one always you have to keep in your mind, which is we can say armature control DC servo motor is inherently a closed loop system because there is a feedback from output to input, whereas field control DC servo motor is an open loop system because there is no feedback from output to input. The next point is phase lag network can't provide significant amplification over the frequency range of interest. Phase lag network can't provide the significant amplification over the frequency range of interest. So I can say only one important point. What is the meaning of this one? Phase lag network. I've already told you phase lag network is going to improve the steady state response, but it is going to degrade the transient response to a smaller amount of extent. So it is going to provide a negative phase angle for all the frequency range of interest, but it will never provide any amplification. It can only shift the output signal. It can only shift the output signal. It is going to output is always going to let the input as a moment of angle, but it will never provide any amplification. So we can say for the phase lead also, phase network and the phase lag network, they won't provide any amplification, but they can only shift the input signal by small amount of extent. So positive phase shift for the phase lead network and negative phase shift for the phase lag network. So this point always you have to keep in your mind, which is we can say a phase lag network can't provide significant amplification over the frequency range of interest. So we can say the phase lead as well as the phase lag, they can't provide any significant amplification over the frequency range of interest, but they can only provide a phase shift for the input signal. The next point is transfer function with the zeros in the right half of a S-plane is a non-minimum phase system. I've already told you what is a minimum phase system and non-minimum phase system. Minimum phase system means all the poles and zeros are going to lie in the LHS of S-plane, then it is called as a minimum phase system. Only for minimum phase system only the Bode analysis is going to get occur. Only for the minimum phase system only the Bode analysis is going to get happen. Whereas non-minimum phase system is if any zero, if it is going to lie in the axis of S-plane, then we say that is said to be non-minimum phase system. So listen carefully. Minimum phase system means all the poles and the zeros, if they are going to lie in the axis of S-plane, then we say it is said to be minimum phase system. Non-minimum phase system is if some of the zeros are going to lie in the axis of S-plane, then that is called as a non-minimum phase system. Transfer function with the zeros in the right half of a S-plane is a non-minimum phase system. The next point is the stator windings of a control transformer has the lower impedance per phase and rotor of a control transformer is cylindrical in shape. The stator windings of a control transformer has the lower impedance per phase and the rotor of the control transformer is cylindrical in shape. So basically here they are telling you some points regarding the control transformer. So this control transformer, what is going to happen is basically for this control transformer, the stator windings will have the low impedance per phase and the rotor is basically cylindrical in shape. So we can say for this control transformer, the stator windings will have the for this control transformer, the stator windings will have the low impedance per phase and the rotor is basically cylindrical in shape. So these points always you have to keep in your mind for a control transformer. So we can say for a control transformer, the stator windings will be basically it will have low impedance per phase and the rotor will be cylindrical in shape. So these points always you have to keep in your mind, which is we can say that finally for a control transformer, the stator winding is basically it has low impedance per phase, whereas the rotor is a cylindrical in shape. So this one always you have to keep in your mind. So we can say a simple was that for a control transformer, the stator windings has the low impedance per phase and the rotor is basically of cylindrical in shape. So finally in simple words I can say that for a control transformer, the stator winding has the lower impedance per phase, whereas the rotor is basically cylindrical in shape. The next point is in a badly underdamped control system, the type of cascade compensator used to improve damping ratio zeta increases is called as a phase lead compensator. When a badly underdamped control system, underdamped means we can say the oscillations are going to reduce as time goes on. The type of cascade compensator used to improve the damping ratio is a phase shift compensator. So basically suppose there is a very badly underdamped control system. So if you want to keep any compensator in order to improve the damping ratio, then what you will prefer? It is basically phase shift compensator. So suppose let me take some control system. It is having a very badly underdamped control system. Means we can say it is having the we can say oscillations are going to get reduced. So as oscillations are going to get reduced. So now what type of compensator I should keep in this control system in order to improve the damping ratio, which is the phase lead compensator. So we can say in simple words that suppose there is a very badly underdamped control system is there. So we can say the oscillations are going to reduce with respect to time. So for this one, suppose what type of compensator I should keep here in this control system in order to improve the damping ratio means damping ratio zeta should increase with the help of what compensator, which is basically phase shift compensator. I've already told you the phase shift compensator is going to improve the transient response and it is going to decrease the steady response to a smaller amount of extent. And also we can say it is going to provide the positive phase shift in the output signal, so output is going to always lead the input. Output is always going to lead the input. And also I've already told you in the case of the phase shift compensator, the zero is always closer to origin when compared to pole. So these things I've already told you. Finally I can say whenever a badly underdamped control system whenever a very badly unadapt control system is there, and if whatever compensator you should keep in this control system in order to improve the damping ratio, which is the phase-heavy compensator. So the phase-heavy compensator, the damping ratio is always going to get increased. So this one I already told you so many number of times. The next point is, in the position control systems, a tacho generator is basically used for providing the rate feedback. In the case of position control systems, the tacho generator is basically used for providing the rate feedback, because for tacho generator the input is the mechanical rotation and the output is the DC voltage. So here is the proportional to rate of change of velocity, angular velocity. So because of this one you can say the input is a mechanical rotation and the output is a DC voltage. So therefore we can say in the position control systems, the tacho generator is basically used for providing the rate feedback. Rate means derivative of the speed. So we can say finally, in position control systems, the tacho generator is basically used for providing the rate feedback. So in the case of position control systems, the tacho generator is basically used for providing the rate feedback. So we can say for tacho generator, the input is the mechanical speed and the output is the DC voltage. So therefore we can say in the case of position control systems, the tacho generator is basically used for providing the rate feedback. The next point is the larger and more sophisticated aircrafts have AC systems operating at 4 nodes. If we use higher frequency, the weight of the components reduces. Larger and more sophisticated aircrafts have AC systems operating at the 400 Hz. If we use higher frequency, the weight of the components will decreases, because I already told you weight is always inversely proportional to frequency. So weight of the components is always inversely proportional to the frequency. So whenever you are going to increase the frequency, the weight of the devices are going to get reduces. So therefore we can easily use this in the aircrafts. So larger and more sophisticated aircrafts have the AC systems. It is operating at the 400 Hz. So if you use higher frequency, the weight of the components reduces, because you can see clearly weight is always inversely proportional to frequency. So as the frequency increases, the weight is going to get reduces. So because of this only, we can say that whenever we are going to operate the more frequency, the weight of the components are going to get reduces. So lesser weight means we can use those weights in the aircraft systems. So finally I can say, whenever you are going to increase the frequency of the operation, the weight of the component is going to get reduces. So less weight means we can use it in a aircraft applications also. There we require less amount of weights. So finally in simple words I can say, whenever you are going to increase the frequency range of operation, then weight of the component is going to get reduces. So therefore lesser weight means we can use those things in the aircraft applications, because there it requires less amount of weights. So finally I can say larger and more sophisticated aircrafts have the AC systems which are basically operating at the 400 Hz. If we use higher frequency, the weight of the components are going to get reduced, because weight is always inversely proportional to the frequency. So finally I can say larger and more sophisticated aircrafts have the AC systems which are operating at the 400 Hz. And if we use the higher frequency, the weight of the components are going to get reduced, because weight is always inversely proportional to the frequency. So as the frequency increases, the weight of the component is going to get reduces. So those less weights we can use in the aircraft applications. We are going to discuss the another point, which is the if the rotor resistance of the servo motor is low, then the torque speed characteristics will be non-linear, and if it is high, then characteristics will be linear, and then having over a wide range of speed, and it has better accelerating characteristics. See, this point I already told you yesterday. I already told you. Suppose if you want a linear torque speed characteristics, then definitely the XBR ratio should be very, very low of the servo motor. Low means R should be very high. So R is equal to high. The rotor resistance must be very, very high, and the rotor reactance must be very, very low. So this point always you have to keep in your mind. So now we will see what is going to happen. Suppose if the rotor resistance of the servo motor is low, then what is going to happen? the SPR ratio is very, very high. So definitely you are not going to get a linear graph, or we can say we are going to get a non-linear graph between the torque and the speed. So then the torque speed characteristics will be non-linear in nature. And if it is high, means the resistance is high, means the SPR ratio is very, very lesser, then the characteristics will be linear and then have the over wide range of speed, and it has the better aspirating characteristics. So I can say simple words. Suppose for a given servo motor, suppose if the resistance of the rotor is very, very high, then what is going to happen? When SPR ratio is very, very less, then we are going to get the linear characteristics between the torque and the speed. So you are going to get a very better aspirating characteristics also. Suppose if the resistance is very, very less, then SPR ratio is very, very high, then you are going to get a no linear characteristics between the torque and the speed. So these programs you have to keep in your mind. So finally I can say, for a given servo motor, if the rotor resistance is high, means the SPR ratio is very, very low. So therefore we can say we are going to get the linear graph between the torque and the speed. Linear graph between the torque and the speed, and you are going to have the better aspirating characteristics. Suppose if the rotor resistance is very, very less, then SPR ratio is very, very high. So you are going to get a non-linear graph between the torque and the speed. So this one always you have to keep in your mind. The next point is an effect of phase lag compensation on servo system performance is that for a given relative stability, the velocity constant is increased. An effect of phase lag compensation on servo system performance is that for a given relative stability, the velocity constant is increased. So, the effect of phase lag compensation on the servo system performance is that for a given relative stability, the velocity constant is increased. So, what is the velocity constant? kV. Velocity constant means we can say kV. So, if you want a relative stability, suppose if you want the stability to increase, then definitely the velocity constant is also increased by using the phase lag compensation on the servo system. So whenever you are going to use a phase lag compensation on the servo system, and if you want a better stability, then definitely the velocity constant is also increased. So you can see, whenever you are going to use the phase lag compensation on the servo system, then the stability is going to get increases, as well as the velocity constant kV is also going to get increases. So therefore we can say in simple words that the effect of, we can say, whenever you are going to use a phase lag compensation on the servo system performance, then if you want the relative stability to increase, then velocity constant is also increased. So finally in simple words I can say, suppose if you are going to use the phase lag compensation on the servo system, then if the relative stability increases, then the velocity constant is also increases. So finally I can say, if you are going to use the phase lag compensation on the servo system, if you want to have a very better relative stability, then the velocity constant is also going to get increases. So finally I can say that if you are going to use a phase lag compensation on the servo system, so because of this, if the stability increases, then the velocity constant kV is also going to get increases. So finally in simple words I can say like this. Which is basically, suppose if you are going to use a phase lag compensation on the servo system, and if you want the stability to get increased, then the velocity constant kV is also going to get increases. So finally in simple words I can say like this, which is, suppose if you are going to use the phase lag compensation on the servo system, as the stability increases, then the velocity constant kV is also going to get increases. Then the next point is, in a closed loop system, the output is speed of a motor, and the output rate control can be used to limit the speed of the motor. So in a closed loop system, the output is speed of the motor, and the output rate control can be used to limit the speed of the motor. Suppose if I am going to take some closed loop system, in this closed loop system the output is the speed of a motor. So suppose if you are going to use a rate feedback control, then what you are going to do basically with the help of this rate feedback control, you are going to control the speed of the motor. So with the help of this rate feedback control, we are going to control the speed of the motor. So therefore we can say, in a closed loop system, the output is the speed of the motor, and the output rate control can be basically used to limit the speed of the motor. So basically here what I am going to tell you in simple words. Suppose let me take some closed loop system. For this closed loop system, the output is the speed of the motor. Suppose now I am going to use suppose if I am going to use the rate feedback control, then by this we are going to control the speed of this motor. So finally I can say in simple words, suppose if I am going to take some closed loop system. For this closed loop system, the output is the speed of the motor. Then with the help of this output rate feedback control, basically we are going to control the speed of the motor, because here basically with the help of output rate feedback control means if the input is basically we can say it is a taper generator. The input is a mechanical rotation and output we are going to get a DC voltage. So with the help of this we are going to control the speed of the motor. The next point is that the correct sequence of steps needed to improve the system stability is use the negative feedback, reduce the gain as well as zeta inside derivation action and inside the derivation action. So basically the correct sequence of steps needed in order to improve the system stability is use the negative feedback, then reduce the gain and also inside the derivative action. I already told derivative action is PD controller. PD controller is going to increase the stability because it is going to add the zeros. So inside derivative action means PD controller or derivative controller. So derivative controller means it is going to give you zeros. So whenever you are going to insert a zeros, definitely the root cause is going to shift the LS of S plane. So therefore we can say the system will become more stable. So therefore we can say in simple words that the correct sequence of steps needed in order to improve the system stability is use the negative feedback or reduce the gain as well as insert the derivative action. So the first step, if the first step in order to improve the system stability is use the negative feedback or reduce the gain or insert the derivative action, or and derivative action is PD controller, because PD controller is going to insert the zeros. So if we are going to insert the zeros means we can say the root locus is going to shift the LS of S plane. So therefore the system will be more stable. So finally I can say the correct sequence of steps needed to improve the system stability is basically use the negative feedback, reduce the gain as well as insert the derivative action. The next point is, with the effect of integral controller, the steady state error and the relative stability both are going to get reduces. With the effect of integral controller, the steady state error as well as the relative stability both are going to get reduces. I already told you, integral controller means lag compensator. Lag compensator is called as integral controller, whereas the derivative controller is called as a lead controller. I already told you. So this integral controller is basically, or the lag controller is going to improve the steady state response, means it is going to decrease the steady state error. And see, basically integral means it is a 1 by terms, means poles are going to get added. So if the poles are going to get added to the open loop transfer function, we can say the root locus is going to shift to the arc of S plane. So therefore the system will become unstable. So therefore stability is also going to get reduces. So therefore we can say with the effect of the integral controller, the steady state error as well as the relative stability both are going to get reduces. So with the effect of the integral controller as well as the steady state error as well as the relative stability both are going to get reduces. So finally I can say that with the effect of the integral controller, the steady state error as well as the relative stability both are going to get reduces, because integral controller means it is basically the lag compensator. So lag compensator means it is an integral controller. So with the help of integral controller, we are going to add the poles. So whenever we are going to add a poles to open loop transfer function, the root locus is going to shift the arcs of S plane. The system will become unstable, or we can say the stability is going to get reduces. Whereas the lag compensator is basically used to improve the steady state response and is going to deviate the transient response to a smaller extent. So therefore we can say finally the steady state error is going to get reduces. So finally I can say with the effect of integral controller, the steady state error as well as the relative stability both are going to get reduces. The next point is, the state feedback design is more realistic than conventional fixed configuration controller design because the disadvantages with the state feedback is that all the states must be sensed and feedback for control. The state feedback design is more realistic than the conventional fixed configuration controller design because the disadvantages with the state feedback is that all the states must be sensed and feedback for control. You can say the state feedback design is more realistic than the conventional fixed configuration controller design because the disadvantages with the state feedback is that all the states must be sensed and feedback for the control. So basically, what I am trying to tell you is a state feedback design is somewhat more realistic than the conventional fixed configuration controller design. So basically, controller design, we can do by two methods. One is the state feedback design as well as the conventional fixed configuration. Out of this, state feedback design is more realistic. And also, in the case of state feedback, that all the states should be sensed and they should be feedback for the control. So basically, we can say with the help of, in the case of state feedback, all the states must be sensed and they are sent for the feedback and they are feedback for control. So we can say the state feedback design is more realistic than the conventional fixed configuration control design because the disadvantage of the state feedback is that all the states must be sensed and they are feedback for the control. So in simple words, I can say basically there are two methods in order to design the controller. One is the state feedback design and the other is the conventional fixed configuration. Out of this, state feedback design is more realistic when compared to conventional fixed configuration. So now, whereas in the case of state feedback design, all the states should be sensed and also they should be feedback for the control. So in the case of state feedback, all the states must be sensed and also they are feedback for the control. So this one always you have to keep in your mind. So this is the only disadvantages. So here, because you have to remove, here because this is not the explanation, basically they are telling you here some important point. So because you should remove this one. So in simple words, I can say that there are two methods for the controller design. One is the state feedback design and the other is the, we can say, and the other is the conventional fixed configuration. Out of this, state feedback design is more realistic when compared to conventional fixed configuration. Whereas the disadvantage of the state feedback design is that in this, all the states are sensed and also they are feedback for the controller. So this is the most disadvantages in the case of state feedback design. So finally I can say there are two methods for designing the control, which are the state feedback design as well as the conventional fixed configuration. Out of this, state feedback design is more realistic when compared to conventional fixed configuration. Whereas one of the most disadvantages of the state feedback is that here in this, all the states must be sensed and also they are feedback for the control. So this is one of the disadvantages of the state feedback because in the case of state feedback, the most important disadvantage is here, all the states must be sensed and also they are feedback for the control. So this one always you have to keep in your mind. Now the next point is time response of an indicating instrument is decided by the damping system. The time response of an indicating instrument is basically decided by the damping system. Yes, that is always true. Why? Because like this. Basically, if you say clearly, see whenever the damping is more means, see whenever the suppose damping is more. So if the damping of the system is more, then what is the meaning of this one? Damping ratio is very more. Then the outputs are going to be decreased in a less amount of time. So the output is going to be that steady state in less amount of time. Suppose if the damping ratio is very less, and what is going to happen? There will be a lot of oscillations and the output is going to take a lot of time in order to reach the steady state. So listen carefully. If the damping of the system is very more, yes, the damping ratio is very high, then the oscillations are going to die in a less amount of time. So you are going to get the output in a very less amount of time. You are going to get the steady state value. Suppose if the damping ratio is very less, then what is going to happen? If the damping ratio or the damping of the system is very less, then there will be a lot of oscillations and the output will take a lot of time in order to reach the steady state value. So these things always you have to keep in your mind. So therefore we can say the time response of an indicating instrument is basically decided by the damping system. So we can say the time response of an indicating instrument is basically decided by the damping system. So finally I can say the time response of an indicating instrument is basically decided by the damping system. The next point is, since lead compensation increases the margin of stability, so we use higher order systems with the lead compensation. Since the lead compensation increases the margin of the stability, so we use higher order systems with the lead compensation. So in this question, in this point, they are saying that since lead compensation is going to increase the margin of the stability, so we use higher order systems with the lead compensation. So what is the point saying is that suppose whenever you are going to use the lead compensation, it is going to increase the margin of the stability. So we use the higher order systems with the lead compensation. So basically what I am trying to tell you, say what I told you, lead compensation means, the lead means we can say PD controller. So lead means the zero is closer to origin when compared to pole. So with the help of lead compensation, we are going to add a dominant zero but a insignificant pole. So because of this, we can say the root locus is going to shift to the LS of S plane because of dominant zero. So system stability is going to get increases. So therefore we can say the stability is going to get increases or the marginal stability is going to get increases. So that is the reason we use the lead composition for the only for the higher order systems. Only for the higher order systems. Similarly, the phase lag compensation is going to decrease the margin of stability, so it is used for low order systems. So this point always you have to keep in your mind. So listen carefully. As I already told you, lead compensation, here in this one, there is a dominant zero and a significant pole. So whenever you are going to add dominant zero, definitely the root locus is going to shift to the LS of S plane. So therefore the system stability is going to get increases. So therefore we can say with the help of lead compensation, the stability of the system is going to get increases. So that is the reason we use this lead compensation only for the higher order systems. Whereas the phase lag compensation, it is basically we are going to have a dominant pole when compared to insignificant zero. So because of this, the stability is going to get decreases. So because of this reason, we are going to add for the phase lag compensation for low order systems. So this point always you have to keep in your mind. The next point is in type 0 and type 1 systems, stable operation is possible if gain is suitably reduced because any one of the compensators lag lead may be used to improve the performance. So in type 0 and type 1 systems, stable operation is possible if gain is suitably reduced because any one of the compensators lag lead may be used to improve the performance. So what I am trying to tell you is very simple. In the case of type 0 and type 1 systems, stable operation is possible if gain is suitably reduced because any one of the compensators lag lead may be used to improve the performance. And what I told you, if you want to increase the range of stability, definitely you have to decrease the range of the gain as well as you have to add the zeros. So this point I have already told you so many number of times. So in type 0 and type 1 systems, stable operation is possible if the gain is stably reduced because any one of the compensators say that lag lead may be used to improve the stability performance. So finally I can say that I have already told you if you want to increase the range of stability, we have to basically what you have to do, we have to reduce the range of the gain as well as we have to add the zeros in order to make the system to become stable. So in type 0 and type 1 systems, stable operation is possible if the gain is suitably reduced because any one of the compensators like lag lead may be basically used to improve the performance. So finally I can say in type 0 and type 1 systems, stable operation is possible if gain is suitably reduced because any one of the compensators like lag lead may be used to improve the performance. The next point is, in PD compensation, zeta increases whereas the omega n is equal to constant. So I already told you what is the meaning of proportional derivative. Proportional derivative means lead compensator. Because shortcut I already told you, in the lead D is there, in the PD also D is there. So lead compensator is always used to improve the transient response, or it is going to degrade the steady state response to a smaller amount of extent. So this one I already told you so many number of times. So it is going to improve the transient response means, it is going to improve the speed of the response means, the rise time is going to get decreases, whereas the bandwidth is going to get increases because both are, the product is always equal to constant. If one is going to increase, means the other will decrease. I already told in all the three cases, the damping ratio is going to get increases. So therefore, the peak portion is going to get decreases because both are inversely proportional. And this one is the omega n is equal to constant. The natural frequency will never change with the help of PD compensation. So these points always you have to keep in your mind. So in the case of PD compensation or the lead compensation, we can say the rise time decreases, the bandwidth increases, the damping ratio increases, the peak portion decreases, whereas the natural frequency omega n is always equal to constant. It will never get changed. The next point is only lag compensator is used to compensate the steady state error. I already told you, lead compensator is always used to improve the transient response of the system, whereas the lag compensator is used to improve the steady state response of the system. So this one I have already told you so many number of times. So this is basically lead and this is the lag. So lead means I have already told you transient has more number of volts, whereas the steady has less number of volts. So match two things of more volts and match two things of less volts. So lead compensator is used to improve only the transient response and it is going to degrade the steady state response to a smaller extent. Whereas the lag compensator is used to improve the steady state response, but it is going to degrade the transient response to a smaller amount of extent. So we can say improving the steady state response means decreasing the steady state error. So therefore we can say only lag compensator is basically used to compensate the steady state error. The next point is phase lag network has dominant pole, thus it will reduce bandwidth. Whereas a phase lag network has dominant zero, thus it will increase the bandwidth. So listen carefully. I already told you. See, listen carefully. In the case of phase lag network, so in the phase lag network means we can say phase lag network means I already told you. Phase lag network means is going to improve the steady state response and is going to decrease. It is going to degrade the transient response. Degrading the transient response means the transient time will increases. So transient time, we can say the rise time is going to get increases. So because of this, the bandwidth is going to get reduces. So it will reduce the bandwidth. Whereas in the case of phase lag network, it has a dominant zero and insignificant pole. So because of this, I already told you, the ASL compensator is used to improve the transient response, but it is going to degrade the steady state response. Improving the transient response means the rise time decreases, whereas the bandwidth will increase. So this you can see clearly from this picture. So therefore we can say, finally, phase lag network, basically, it is used to improve the transient response and is going to degrade the steady state response. Improving the transient response means increasing the speed of the response means rise time decreases, so bandwidth will increase. Whereas in the case of phase lag network, it has a dominant pole and insignificant zero. So because of this, what is going to happen? We can say it is going to improve only the steady state response, but it is going to degrade the transient response means the rise time is going to get increases, so bandwidth will decreases. So finally I can say, in the case of phase lag network, the bandwidth increases, whereas in the case of phase lag network, the bandwidth will decrease. So this point you can see clearly from this picture. The next point is, the inductors is not used to fabricate a lag network as it produces time delay and hysteresis loss. So capacitors are used to design the phase lag network. The inductors is not used to fabricate a lag network as it produces time delay and hysteresis losses. So capacitors are used to design the phase lag network. So basically, in this question, in this point they are saying that, see, in order to make the phase lag network, we are not going to use the inductor. So you can see clearly in the picture also, I have already told you the initial concept. how to design the phase lag network, how to design the phase lag network. I've already told you with the picture also. I've already told you that with the picture also. In that we are not going to use any inductor only, we are going to use the capacitor only. In that picture only I've already told you. In the case of phase lag as well as phase lag, we are not going to use any inductors, but we are going to use only the capacitors. Why? Why we are not going to use inductors? Because it is going to produce us some time delay as well as some hysteresis losses. So because of this, we are not going to use the inductors. So this one always you have to keep in your mind. So basically, we can say the inductors are basically we are not going to use in the case of phase lag network as well as phase lag network, because with the help of inductors there will be small amount of time delay as well as hysteresis losses. So because of this reason only, we are not going to use any inductors in the case of phase lag network. We are going to use only capacitors in the case of phase lag as well as phase lag, because inductors are going to produce the time delay as well as the hysteresis losses. So because of this reason only, we are not going to use the inductors in the phase lag as well as the phase lag network. So this point always you have to keep in your mind. So therefore we can say, I've already told you how to design the phase lag network as well as phase lag network. I've already told you where we are not going to use any inductors. We are going to use only capacitors to design the phase lag as well as the phase lag. So basically, we can say in simple words, inductors we are not going to use because it is going to produce some time delay as well as hysteresis losses. So because of this reason, we are not going to use the inductors in making the phase lag as well as phase lag. So finally, I can say the inductors is not used to fabricate a phase lag network as well as phase lag network because it is going to produce some time delay as well as hysteresis losses. So because of these reasons only, we are going to use the capacitors in order to design the phase lag network as well as the phase lag network. So these points always you have to keep in your mind. We are going to discuss the other point, which is the characteristics of a derivative controller. So we are going to discuss some characteristics of the derivative controller, which is if the error is 0, then output from the controller is 0. Yes, derivative of any 0 is equal to 0. So therefore, what is the meaning of derivative controller? Suppose input, so output is the derivative of the input. So derivative controller means output is the derivative of the input. Derivative of the input, that is called as the derivative controller. So output is the derivative of the input, that is the reason it is called as a derivative controller. So if the error is 0, means if the input is 0, then the output from the controller is 0 because the derivative of 0 is equal to 0. So therefore we can say if the input is equal to 0, input is nothing but error. So if the input is equal to 0, so output is also equal to 0. If error is constant in time, then output from the controller is 0. If error means input, if input is constant in time, then derivative, then the output from the controller is 0 because derivative of a constant term is equal to 0. So therefore, whenever the error of the input is a constant with respect to time, and the derivative of the constant is equal to 0, so from the output is nothing but 0. Suppose the next point is, for changing error in time, the output from the controller is amount of k percentage for every 1% second inverse per rate of change of error. So basically here we can see the exact expression. What is a so what is the exact expression of derivative controller? Output is equal to k into derivative of the input. So this is the exact expression. Suppose if the input is changed by 1%, then output is changed by k percentage, amount of the k percentage. Derivative is if the input is increased, means the output is also increased. If the input is decreased, means the output is also decreased. So if the input is increased by 1%, then the output is increased by k percentage. If the input is decreased by 1%, then the output is also decreased by k percentage. So this you can say this is the exact expression of the output and input of the derivative controller. So for changing error in time, the output from the controller is amount of the k percentage for every 1% second inverse rate of change of error. Means for 1% rise in error, the output is also changed by plus k percentage. Suppose if the input is decreased by 1%, then the output is also decreased by k percentage. The next point is, for positive range of change of error, the output is also positive. Yes. Suppose if the input is increasing, the output is also increasing. If the input is decreasing, the output is also decreasing because the derivative of increasing function is increasing. derivative of decreasing function is equal to decreasing. So therefore we can say both are having a similar nature. So for positive rate of change of error, the output is also positive. For negative rate of change of error, the output is also negative. So this one we can see clearly from this expression. So we can say some of the characteristics of a derivative controller, which is if the error is 0, then the output from the controller is 0. If the error is constant in time, then the output from the controller is 0. For changing error in time, the output from the controller is magnitude of k percentage for every 1%, second inverse rate of change of error. For positive rate of change of error, the output is also positive. For negative rate of change of error, the output is also negative. So these things always you have to keep in your mind. The next point is frequency response analysis implies varying omega from 0 to infinity and observing the corresponding variations in the magnitude and the phase angle of the response. Frequency response analysis implies varying omega from 0 to infinity and observing the corresponding variations in the magnitude and the phase angle of the response. So what is the meaning of frequency response analysis? Means we are going to vary the frequency from 0 to infinity. Then what is the variation in the magnitude and the phase angle? That is called the frequency response. So frequency response analysis means basically we are going to change omega from 0 to infinity. By changing omega from 0 to infinity, then what is the variation in the magnitude as well as the phase angle of the response that we are going to plot? That is called the frequency response analysis. So in simple words I can say like this. Frequency response analysis means whenever you are going to change the frequency omega from 0 to infinity, then there is a change of the magnitude as well as the phase angle. So what is the variation? That is called the frequency response analysis. So frequency response analysis means whenever you are going to change the frequency omega from 0 to infinity, then what is the variation of the magnitude as well as the phase angle of the response that we are going to see. That is called the frequency response analysis. So frequency response analysis implies varying omega from 0 to infinity and observing the corresponding variations in the magnitude as well as the phase angle of the response. The next point is, in control systems always do calculation in the radian mode. I already told you, in the control systems always you are doing calculations only in the radian mode. So this one I have already told you so many number of times. So basically I can say that in the control systems always we will do the calculations only in the radian mode. So in the control systems always we have to do the calculations only in the radian mode. So this one always you have to keep in your mind. So we can say in the case of control systems always we are going to do the calculations only in the radian mode. The next point is 1 by root 2 is nothing but 0.707 and 1 by 2 to the power of 1 by 4 is nothing but 0.18. So listen carefully. 1 by 4th root of 2 is equal to 0.84. So this one you have to keep in your mind. So 1 by 4th root of 2 is equal to 0.84, whereas 1 by root 2 is equal to 0.707, because some examinations they will never allow you to use a calculator. So because of this reason only I am making these values to remember. So you have to remember these values because in the examinations this will be very much useful in order to solve the questions. Because in some examinations they are not going to allow the calculator. So it is better for you to remember these values. 1 by root 2, 0.707 and 1 by 4th root of 2 is equal to 0.84. So these two things always you have to keep in your mind. Which is 1 by root 2 is equal to 0.707 and 1 by 4th root of 2 is equal to 0.84. So these two values always you have to keep in your mind. So finally I can say 1 by root 2 is equal to 0.707 and 1 by 4th root of 2 is equal to 0.84. So we can say 1 by root 2 is equal to 0.707 and 1 by 4th root of 2 is equal to 0.84. So these things always you have to keep in your mind. The next point is, when gain margin is equal to phase margin, it means that system is marginally stable. So AD is equal to BC. I have already told you, suppose the characteristic equation is AS cube plus BS square plus CS plus D, then I have already told you, if AD is less than BC, AC the system is said to be stable. And also some more points here in stability, which is stability, the gain crossover frequency is equal to phase crossover frequency. I already told you. And also, which is the gain margin and phase margin both are positive, as well as the gain margin is lesser than the phase crossover frequency. See, listen carefully. For a system to be stable, AD is less than BC, and the gain crossover frequency is lesser than phase crossover frequency, as well as gain margin and phase margin both are stable, or both are positive. Similarly, suppose if AD is equal to BC, AC in the system is said to be largely stable, and the gain crossover frequency is equal to phase crossover frequency, and the gain margin is equal to phase margin is equal to 0. Whereas if AD is greater than BC, then we can say the system is said to be unstable, and also the gain crossover frequency is greater than phase crossover frequency, and the gain margin and phase margin both are negative. So this one's always you have to keep in your mind. So finally I can say that for a characteristic equation ESP plus BSP plus CS plus D is equal to 0, we can say for a system to be stable, AD is less than BC. Then when the system is stable, as some more points are, the gain crossover frequency is lesser than phase crossover frequency, whereas the gain margin and phase margin both are positive. And whenever AD is equal to BC, the system is said to be marginally stable, whereas the gain crossover frequency is equal to phase crossover frequency, and the gain margin and phase margin both are equal, and it is equal to 0. So for a system to become unstable, the A into B is always greater than B into C. And also the gain crossover frequency is greater than the phase crossover frequency, and the gain margin and both and the phase margin both are negative. So these things always you have to keep in your mind. So here less means here also less, here equal means here also equal, here greater means here also greater. So these things always you have to keep in your mind. Say I have already told you G of j omega h of j omega is a complex number. It will have the magnitude as well as a phase angle. So magnitude of G of j omega h of j omega, phase angle of G of j omega h of j omega. So basically this G of j omega h of j omega is a complex number. It will have the magnitude as well as the phase angle. So I have already told you gain crossover frequency is the frequency at which the magnitude of the upper transfer function is equal to 1. And phase crossover frequency is a frequency at which the phase angle of the upper transfer function is equal to minus 180 degree. So this one I have already told you so many number of times. So listen carefully. The gain crossover frequency is a frequency at which the magnitude of the upper transfer function is equal to 1. Whereas the phase crossover frequency is a frequency at which the phase angle of the upper transfer function is equal to minus 180 degree. So these things always you have to keep in your mind. Now the next point is, I have already told you when the gain crossover frequency is greater than phase crossover frequency, then we are going to get the gain margin in dB as well as the phase margin in degree. Both are going to get negative. So therefore we can say the system is said to be unstable. Just now we have discussed. I have already told you for a characteristic equation ASQ plus BSQ plus CS plus D equal to 0. Whenever AD is less than BC, we say the system is said to be unstable. It is said to be stable, and some more important point is the gain crossover frequency is lesser than phase crossover frequency. Both the gain margin and the phase margin both are said to be positive. Whenever AD is equal to BC, we say the system is said to be marginally stable. Therefore, the gain crossover frequency is equal to phase crossover frequency. Both the gain margin and the phase margin both are equal to 0. And whenever AD is greater than BC, we say the system is said to be unstable. So therefore, the gain crossover frequency is greater than phase crossover frequency. Both the gain margin and phase margin both are negative. Same thing we can see clearly on this picture also. So now the next point is, what is the procedure to calculate the gain margin? So now I am going to tell you the actual procedure in order to calculate the gain margin, which is G of j omega h of j omega is equal to the magnitude of G of h of s phase angle of G of h of s. So basically you can see G of h of s is basically a clock. It is a complex thing, complex value. So we have the magnitude as well as we have the phase angle. So now I am going to find the phase crossover frequency. Phase crossover frequency, it is the frequency at which the phase angle of G of h of s is equal to minus 180 degree. So from this one try to get the value of phase crossover frequency. And what is the gain margin? I have already told you gain margin formula. I have already told you the gain margin is equal to 1 by magnitude of G of s h of s, and the gain margin is phase crossover frequency. So if you want the gain margin in dB, then you have to keep your 20 log gain margin the base 10. So this we are going to get the gain margin in dB. So if you substitute, if you simplify, we are going to get finally minus 20 log magnitude of g of h of s at the phase cost of frequency with a base of 10. So this we are going to get in terms of dB. So therefore we can say, I've already told you this procedure always you have to keep in your mind. So this procedure is going to tell you in this way you have to find the gain margin in dB, which is the g of h of s is the complex number to like the magnitude of the phase angle. Phase cost of frequency is the frequency, which is the phase angle of g of h of s. We are going to get its value is equal to minus 1 degree. And the gain margin in dB is something which is equal to gain margin is equal to 1 by the magnitude of open loop transfer function, the phase cost of frequency. So if you want the gain margin in dB, then you have to substitute 20 log gain margin in 10 to the base 10. So if you have to simplify, we are going to find minus 20 log of mod g of h of s at the phase cost of frequency to the base 10 in dB. The next point is, if polar plot encloses the minus 1 plus j0 point, then the system is said to be perfectly unstable. As I already told you, if the polar plot is not going to enclose the minus 1 plus j0, we say the system is said to be stable. If the polar plot is going to cut the passes through minus 1 plus j0, then we say the system is said to be marginally stable. If the polar plot is going to enclose the minus 1 plus j0, then we can say the system is said to be perfectly unstable. So this point always you have to keep in mind. Suppose enclosing means enclosing minus 1 plus 0 means shortcut. Remember I already told you, if you are eating something very high, definitely you will become unstable in health. Your health will become unstable. If you eat something very huge quantity, definitely your health will become unstable. So therefore we can say same thing, shortcut to remember. So if the polar plot is not going to enclose the minus 1 plus j0 means the system is said to be stable. If the polar plot is going to cross the minus 1 plus j0 means the system is said to be marginally stable. If the polar plot is going to enclose the minus 1 plus j0 means we can say the system is said to be perfectly unstable. I have already told the shortcut. If you are enclosing something, if you are eating something very high, definitely you will become unstable in terms of health. Here also same thing, the shortcut to remember. So therefore finally I can say, if the polar plot is not going to enclose the minus 1 plus j0 point means the system is said to be stable. If the polar plot is going to cross through minus 1 plus j0 means the system is said to be marginally stable. If the polar plot is going to enclose the minus 1 plus j0 means the system is said to be perfectly unstable. The next point is S is equal to sigma plus j omega, which is equal to r into the power of j theta. Means S is nothing but sigma plus j omega. It's a complex number. It will have the magnitude as well as the phase angle. So what is the magnitude value? I can write the magnitude value, which is equal to under root over sigma square plus omega square. And what is the angle? Angle is equal to tan inverse of omega by sigma. So like this you can write either you can write like this one, or either you can write like this theta also. R is the magnitude, the power of j theta, or r angle theta also you can write r angle theta, r into the power of j theta, and both are same. We can write either in this fashion. This is a polar form, and this is the rectangular form, and this is the polar form. So this one always you have to keep in your mind. The next point is minus 1. How we are going to write the minus 1? Minus 1 is nothing but the magnitude is 1 and the phase angle is minus 180 degree. Minus 1 means the magnitude is 1 and the phase angle is minus 180 degree. So use this always in the case of Lipschitz plot. Lipschitz plot is nothing but it's a combination of the polar plots only. So combination of polar plots is nothing but Lipschitz plot. So minus 1 is nothing but the magnitude is 1 and the phase angle is minus 180 degree. The next point you have to remember, n is equal to p minus z. So this formula always you have to keep in your mind. N is equal to p minus z. Where z indicates the number of closed loop poles in the RHS that we can get from the Rao-Tharber's criteria. Whereas p is the number of poles of open loop transfer function which are present in the RHS of S-plane. Whereas n indicates the number of encirclements around the minus 1 plus j0 in the g of s h of s plane by the Lipschitz plot. So this formula always should be keeping in mind. So we can say n is equal to p minus z. So n is equal to p minus z. So we can say n is equal to p minus z. Where z indicates the number of closed loop poles which are going to present in the RHS that we can get from the Rao-Tharber's criteria. Whereas p indicates the number of poles of the open up transfer function which are going to present in the RHS of S plane. And n indicates the number of encirclements which are present around the minus 1 plus j0 in the open up transfer function by the Nyquist law. So finally I can say n is equal to p minus z. Where z indicates the number of closed loop poles. Means the number of closed loop poles means the roots of the characteristic equation 1 plus g of h of is equal to 0. This number of closed loop poles which are basically present in the RHS of S plane that we are going to get with the help of the Raoult-Tharras criterion. Whereas p indicates the number of poles of the open loop transfer function which are present in the RHS of S plane, and n indicates the number of encirclements which are basically around the minus 1 plus j0 in the open loop transfer function g of h of S plane by the Nyquist law. So this point always you have to keep in your mind. Now you can see clearly at point which is n is equal to p minus z, where that indicates the number of closed loop poles in the RHS that we are going to get from the Raoult-Tharras criteria. And p indicates the number of poles of the open loop transfer function g of h of s in the RHS of the S plane. And the n indicates the number of encirclements around the minus 1 plus j0 in the open loop transfer function g of h of s plane by the Nyquist law. So I already told you, if you want the system to be stable, then z should be always equal to 0, means there should be no poles in the RHS of S plane. Then what is the condition? N is equal to p. So finally I can say n is equal to p minus z, where z indicates the number of closed loop poles of the closed loop transfer function of the closed loop. You can say the number of closed loop poles of the characteristic equation in the RHS of S plane that we are going to get from the Raoult-Tharras criteria. And p indicates the number of poles of the g of h of s which are present in the RHS of S plane. And n indicates the number of encirclements which are around the minus 1 plus j0 in the open transfer function g of h of s plane by Nyquist plot. The next point is, I have already told you minus 1. We can write minus 1 in this formula. So magnitude is 1 and the phase angle is minus 180 degree. Or minus 180 degree means we can say minus 5, or we can write like this also. 1 into e to the power of j. What is the angle here? Minus 5. So like this also you can write. So therefore same thing. You can see clearly here. So minus 1 is 1, an angle of minus 180 degree. In terms of radians, if you want to write, you can write 1 at an angle of minus 5. So I can write in the angle function 1 into e to the power of j theta. Theta is equal to minus 5. Same thing you can see clearly here. The next point is here. Stability is always inversely proportional to the gain of the system. The gain of the is also inversely proportional to gain of the system. Phase margin is also inversely proportional to gain of the system, whereas the damping ratio is also inversely proportional to gain of the system, whereas the phase margin is proportional to damping ratio of the system. So we can say damping ratio means simply we can say the phase margin is also inversely proportional to gain of the system. We can say clearly because the damping ratio is very proportional to 1 by k. So phase margin is also proportional to 1 by k. So we can say stability is inversely proportional to system gain. Gain margin is inversely proportional to system gain. Phase margin is inversely proportional to system gain. Damping ratio is inversely proportional to system gain. So phase margin is also inversely proportional to system gain. So these points always you have to keep in your mind. So therefore we can say that stability is inversely proportional to system gain. Gain margin is inversely proportional to system gain. Phase margin is inversely proportional to system gain. Damping ratio is inversely proportional to system gain. And phase margin is also inversely proportional to system gain. So these points always you have to keep in your mind. So where theta is for damping ratio. So phase margin is always proportional to damping ratio. I have already told you, whenever the system gain k increases, the stability will decrease. So you can see, whenever system gain k increases, the stability is going to get decreases. So both are inversely proportional. So you can say stability is always inversely proportional to system gain. Gain margin is inversely proportional to system gain. Phase margin is inversely proportional to system gain. Damping ratio is inversely proportional to system gain. Phase margin is also inversely proportional to system gain. Or simply we can say the phase margin is proportional to damping ratio also. So finally I can say stability is inversely proportional to system gain. gain margin is inversely proportional to system gain. Phase margin is inversely proportional to system gain. Damping ratio is inversely proportional to system gain. And the phase margin is inversely proportional to system gain. And the phase margin is highly proportional to damping ratio. The next point is, if the open loop transfer function g of h of s is equal to 1 by s into 1 plus t1s into 1 plus t2s, then what is the phase crossover frequency? Phase crossover frequency means it is a frequency at which the phase angle of g of h of s is equal to minus 180 degree. So if we simplify, finally we are going to get the phase crossover frequency is equal to 1 by under root of t1 t2. And what is the gain margin? Gain margin means 1 by magnitude of open loop transfer function at the phase crossover frequency. So if we substitute simplify, we are going to get finally the gain margin is equal to T1 plus T2 by T1 T2. It is not in dB, it is not in dB, it is unitless. So you can say finally that for a open loop transfer function g of h of s is equal to 1 by s into 1 plus T1 s into 1 plus T2s, and the phase crossover frequency is equal to 1 by under root of T1 T2, and the gain margin is equal to T1 plus T2 by T1 T2. So these points always you have to keep in your mind. So therefore we can say whenever the open loop transfer function g of h of s is equal to 1 by s into 1 plus t1 s into 1 plus t2s, then the phase crossover frequency is equal to 1 by under root of t1 t2, and the gain margin is equal to t1 plus t2 by t1 t2. So these points always you have to keep in your mind. So therefore we can say that the open loop transfer function g of h of s is equal to 1 by s into 1 plus t1 s into 1 plus t2s, then the phase crossover frequency is equal to 1 by under root of t1 t2, and the gain margin is equal to t1 plus t2 by t1 t2. So these points always you have to keep in your mind. So finally I can say if the open loop transfer function g of h of s is equal to 1 by s into 1 plus t1 s into 1 plus t2s, and the phase crossover frequency is equal to 1 by under root of t1 t2, and the gain margin is equal to 1 by t1 plus t2 by t1 t2. So this is a shortcut formula we have to remember. So finally I can say if the open loop transfer function g of h of s is equal to 1 by s into 1 plus t1 s into 1 plus t2s, then the phase crossover frequency is equal to 1 by under root of t1 t2, and the gain margin is equal to t1 plus t2 by t1 t2. The next point is g of s h of s is stable when no pole of this lie in the RHS. In another way, the polar plot of g of s h of s not encloses the minus 1 plus j0 point in the g of s h of s plane. Listen carefully. G of s h of s is stable when no pole of this lie in the RHS of s plane. In another way also we can say the polar plot of the g of s h of s should not enclose the minus 1 plus j0 point in the g of s h of s plane. So simple words you can listen carefully. Open loop transfer function g of s h of s is said to be stable when no pole of this is going to lie in the RHS of s plane. In another way also we can say the polar plot of the open loop transfer function g of h of s should not enclose the minus 1 plus j0 point in the g of h of s plane. If it is not going to enclose means we can say it is stable. If it is going to cross this minus 1 plus j0 means we say it is a marginally stable. If it is going to enclose the minus 1 plus j0 means the system is said to be unstable. So this one I have already told you so many number of times. So we can say the open loop transfer function g of s h of s is stable when no pole of this is going to lie in the RHS of s plane. In another way also we can say that the polar plot of the g of s h of s is not going to enclose the minus 1 plus j0 point in the g of s h of s plane. So finally I can say that open loop transfer function g of s h of s is said to be stable when no pole of this is going to lie in the RHS of s plane. In another way also we can say the polar plot of the g of s h of s is not going to enclose the minus 1 plus j0 point in the g of s h of s plane. If it is not going to enclose means we can say it is said to be stable. If it is going to cross the minus 1 plus j0 means we say it is said to be marginally stable. If it is going to enclose this minus 1 plus j0 means the system is said to be unstable. So this point always you have to keep in mind. It is possible to have open loop system stable and closed loop system unstable. So basically, I have already told you, suppose if the open loop system and the closed loop system, suppose if it is unstable, then with the help of feedback, we can make it stable. Suppose if the open loop system is stable, with the help of closed loop system, it can also become unstable. So this point always you have to keep in your mind. So this one I've already told you so many number of times also. Suppose if the open loop system is unstable, with the help of closed loop system, we can make it stable also. Suppose if the open loop system is stable, with the help of closed loop system, we can make it unstable also. I've already told you, if you are going to give the feedback in a proper, it can become stable. Suppose if you are not going to give the feedback properly, then it will become unstable. So this one I've already told you. Suppose if you are going to give the feedback in a proper manner, then it will become stable. Suppose if you are not going to give any feedback proper, it will become unstable also. So it is possible to have open loop system stable and a closed loop system unstable. So therefore we can say, finally, suppose if the open loop system is unstable, with the help of closed loop system, we can try to make it stable. Suppose if the open loop system is stable, with the help of closed loop system, we try to make it unstable also. It is vice versa also possible. The next point is, the functions of the Bode plot is open loop magnitude and the phase angle responses for undamped sinusoidal inputs plotted separately as a function of real frequency. The functions of the Bode plot is open loop magnitude and the phase angles responses for an undamped sinusoidal inputs plotted separately as a function of real frequency. Undamped means we can say that the oscillations are going to present for all the time. So basically, I've already told you what we are going to do with the help of Bode plot. So basically, suppose we are going to take some input of undamped means sinusoidal means always the oscillations are going to present for all the time. So if we are going to give these sinusoidal inputs, then what is the output that we are going to get? If we are going to vary the frequency from 0 to infinity, what is the magnitude variation and what is the phase angle variation that we are going to get, that we are going to see in a clear picture manner. So that is a frequency analysis or Bode plot. The magnitude and the phase angle we are going to see when the omega is varying from 0 to infinity. What is the variation with respect to real frequency? What is the variation that we are going to see with respect to real frequency? That is called as a Bode plot. The functions of Bode plot is the open loop magnitude and the phase angle responses for undamped sinusoidal inputs plotted separately as a function of real frequency. So finally I can say, for a given HDI system, if you are going to give a undamped sinusoidal inputs, then if you are going to vary the frequency from 0 to infinity, then what is the variation of the output magnitude and the output phase angle with respect to input? And both these things we are going to analyze with the help of Bode plot. So finally I can say, the functions of the Bode plot in the open loop magnitude and the phase angle responses for the undamped sinusoidal input plotted separately as a function of real frequency. The next point is the functions of the polar plot is open loop responses due to underdamped sinusoidal as a function of real frequency. So the functions of the polar plot is the open loop response due to underdamped sinusoidal as a function of real frequency. So basically, I've already told you, in the case of polar plots, what we are going to do, for open loop transfer function, we are going to take the magnitude and the phase angle. We are going to plot this graph, this locus diagram, and omega is varying from 0 to infinity. The next point is, the functions of the Nyquist plot is open loop response due to damped sinusoidal inputs as a function of complex frequency. So Nyquist plot means basically, we are going to use the polar plots in order to draw the Nyquist plots. The function of Nyquist plots is the open loop response due to damped sinusoidal inputs as a function of complex frequency. Whereas the function of Nicholas chart is a closed loop responses due to sinusoidal inputs as a function of real frequency. So if you see clearly, this Bode analysis, this polar analysis, and the Nyquist plot analysis, all these are for the open loop transfer function only. See, all this Bode plot analysis, polar plot analysis, and the Nyquist plot analysis, all this analysis is only for the open loop system, whereas the Nicholas chart is for the closed loop system. So the functions of the Nicholas chart is that closed loop responses due to sinusoidal inputs as a function of the real frequency. So this one always you have to keep in your mind. So similarly, listen carefully. This Bode plot analysis, this polar plot analysis, and the Nyquist plot analysis, all this analysis is for the open loop systems, whereas the Nicholas chart is for the closed loop systems. Whereas in the case of Bode plot and the polar plot, the frequency is always real frequency. Whereas in the case of Nyquist plot, the frequency is complex frequency, because if you see clearly there, yes, the real part and the imaginary part is also present. In the case of Nyquist plot, we are going to have the four plots. So on the imaginary axis and the axis of the S-plane, where S is called sigma plus j omega. So we have sigma and omega. So basically we have a complex frequency. So therefore we can say here complex frequency is going to present here. Whereas in the Border plot and polar plot, omega is varying from 0 to infinity. So sigma is equal to 0, only omega is varying. So therefore we can say that is a real frequency. Whereas in the Nyquist plot we are going to use the complex frequency, because S is equal to sigma plus j omega. Sigma is not equal to 0. Omega is also not equal to 0. So because of this reason we say it is a complex frequency. Whereas in the case of Border plot, we are going to have a undamped sizable inputs, where here we have a underdamped means the say options are going to decrease as time goes on. Here we are going to use the damped sinusoid. So this one always you have to keep in mind. So finally I can say in the case of mode analysis, polar analysis and the Nyquist analysis, we are going to use this analysis only for the open loop transfer function, whereas the Nicholas-Strat analysis is used for the closed loop systems. In the case of border plot analysis and polar plot analysis, we are going to use the real frequency. Omega is varying from 0 to infinity. Whereas in the Nyquist plot, we are going to use the frequency which is a complex frequency. For border plot, we are going to use the undamped sizable inputs. Whereas for polar plot, we are going to use the underdamped sizable inputs. Whereas for the Nyquist plots, we are going to go for the damped sizable inputs. Here it is undamped, here it is undamped, here underdamped, and this is damped sequence. Undamped, underdamped, damped. So this one always you have to keep in mind. So here it is undamped, here damped, here totally damped. Undamped, underdamped, and damped. So these things always you have to keep in your mind. So whereas the Nicholas-Strat is basically used for the closed loop systems with the real frequency, except Nyquist plot, remaining all things are the real frequencies. Except Nicholas-Strat, all the things are, except Nyquist plots, everything remaining all the things are real frequencies. Whereas except Nicholas-Strat, remaining all are the open loop transfer function, and Nicholas-Strat is only for the closed loop transfer function. So these things always you have to keep in your mind. So finally I can say the functions of border plot is the open loop magnitude and the phase angle responses for the undamped sizable inputs plotted separately as a function of real frequency, whereas the functions of the polar plot is open loop response due to underdamped sizable as a function of real frequency, whereas the function of the Nyquist plot is the open loop response due to the damped sinusoidal inputs as a function of complex frequency, whereas the functions of the Nicholas-Strat is the closed loop response is due to sizable inputs as a function of real frequency. So finally I can say summary, which is basically border analysis, polar analysis, Nyquist analysis is for the open loop transfer function, whereas the Nicholas-Strat is for the closed loop transfer function. Whereas in the case of border plot, polar plot and the Nicholas-Strat, we are going to use the real frequency, whereas in the case of Nyquist plot, we are going to use the complex frequency. So these things always you have to keep in your mind. So here in the border plot, we are going to use the undamped sinusoidal input. Here in the case of polar plot, we are going to use the underdamped sinusoidal input, whereas in the Nyquist plot, we are going to use the damped sinusoidal inputs. And here we are going to use the purely undamped sinusoidal inputs in the case of Nicholas-Strat. So these things always you have to keep in your mind. Now the next point is, for a stable closed loop system, the Nyquist plot of G of S H of S should encircle the -1, J0 point as many times as there are poles of G of S H of S in the right half of the S plane. The encirclements, if there are any, must be made in a counterclockwise direction. So basically here always you have to keep in your mind, which is I've already told you the basic formula. What is the basic formula? Which is N is equal to P minus Z. So this formula always you have to keep in your mind. Well, what is the meaning of N? N means baseline number of encirclements of the G of S in the G of H of S plane which are occur at -1, J0. Listen carefully. The number of encirclements which are occurred in the G of S H of S plane at -1, 0. Here P indicates the number of poles of the G of S, H of S which are present in the right half of the S-plane, whereas Z indicates the number of closed loop poles of the 1 plus G of S, H of S is equal to 0, or we can say the number of closed loop poles which are going to present in the right half of the S-plane. Suppose if you want the system to be stable, then Z should be always equal to 0 because there must not be any closed loop poles in the right half of S-plane. So therefore we can say that its value is equal to 0. So Z is equal to 0, we can say N is equal to P. N is equal to P means the number of encirclements which are occurred in this open loop transfer function plane is equal to number of open loop poles of the open loop transfer function. It is a positive value. Positive value means I have already told you always positive means go for the anti-clockwise, negative means take for the clockwise. So this one I have already told you. So therefore we can say for a stable closed loop system, the Nyquist plot of the G of S, H of S should encircle the -1, J0 point as many times as there are poles of the G of S, H of S in the right half of the S-plane. And the encirclements, if there are any, must be made in the counterclockwise direction. Counterclockwise direction means anti-clockwise direction because N is positive. N is positive means we can see it is a anti-clockwise direction or counterclockwise direction. We can call it anything. So positive means always anti-clockwise direction or counterclockwise direction. Negative means clockwise direction. So this point I have already told so many number of times. The next point is, if the open loop gain function G of S, H of S is a stable function, then the closed loop system may or may not be stable. See, I have already told you this point, I have already told you just now. Suppose if the open loop transfer function and the closed loop transfer function, so this one I have already told you so many number of times. Suppose if the open loop transfer function is unstable, then we can make it stable with the help of closed loop transfer function. Suppose if the open loop transfer function is stable, with the help of closed loop transfer function, we can get an unstable system. So vice versa is possible. So we can say that if the open loop transfer function is unstable, then we can make the closed loop transfer function stable. Suppose if the open loop transfer function is stable, then we can make the closed loop transfer function as unstable. So this one always you have to keep in your mind. So we can say if the loop gain function G of H of S is a stable function, then the closed loop function may or may not be stable. What I told you, it can be stable or it can be unstable also. It can be stable or it can be even unstable also. Suppose if the open loop transfer function is stable, then the closed loop transfer function can be either unstable or it can be stable. So this one always you have to keep in mind. Suppose you can see clearly, suppose if the open loop transfer function is unstable, then the closed loop transfer function can be either stable or it can be either unstable. Similarly, if the open loop transfer function is stable, then the closed loop transfer function can be either unstable or stable. So this one also you have to keep in mind. The next point is, if the loop gain function G of S, H of S is a stable function for a stable closed loop system, the Nyquist plot of G of S, H of S must not enclose the critical point -1, J0. Listen carefully. If the loop gain function G of S, H of S is a stable function. See, what is the meaning of open loop transfer function? Stable function is there are no open loop poles in the right half of this plane. So P is equal to 0. As you can see, N is equal to P minus Z. Here P is equal to 0, they have already mentioned. Because the open loop transfer function is a stable function. And also they are given the closed loop transfer function is also stable function, also they are given. So that is also equal to 0 because there are no poles in the right half of this plane. There are no closed loop poles in the right half of this plane. So that is also equal to 0. So definitely we are going to get N is equal to 0 means there are no more encirclements at -1, J0 in the G of S, H of S plane. So we can say if the open loop gain function G of S, H of S is a stable function for a stable closed loop system, then Nyquist plot of G of S, H of S must not enclose the critical point -1, J0 in the G of S, H of S plane. So finally I can say that if the loop gain function G of S, H of S is a stable function for a stable closed loop system, the Nyquist plot of G of S, H of S must not enclose the critical point -1, J0. So in simple words, I can say that in the point they are given, the open loop transfer function is a stable function. Open loop transfer function is stable system is There are no open loop poles in the right of a H plane. So P is equal to 0. And also they are given the closed loop system is also stable. Means there are no closed loop poles in the right of a H plane. So that is also equal to 0. So if both are 0, then M is equal to 0. Means there are no encirclements in the Nyquist plot. There is no encirclement at minus 1, J0 in the G of H of S plane. The next point is you can see clearly if the Nyquist plot of G of H of S, if it does not intersect the negative real axis, then the gain margin in dB is infinity. Listen carefully. If the Nyquist plot of G of H of S, if it does not intersect the negative real axis, then the gain margin in dB is infinity. So basically, what is the meaning of gain margin? Gain margin is equal to 1 by mod of G of S H of S at omega PC. So phase crossover frequency. So if you see, listen carefully, omega PC means it is a frequency at which the phase angle of open loop transfer function is equal to minus 180 degree. As you can see clearly here, if the Nyquist plot is not going to intersect the negative real axis, means omega PC, it is not, we are not going to get omega PC, because we are not going to get omega PC, because at that whenever the Nyquist plot is going to cut the imaginary axis, then only at that point we are going to get a phase angle of minus 180 degree at that frequency. So definitely we are not going to get that value. So omega PC value we are not going to get here. So if you are not going to get the omega PC, then definitely we are not going to get the gain margin also. Gain margin also we are not going to get. So definitely we can say that the gain margin in dB is equal to infinity. So gain margin in dB means I have already told you 20 log gain margin with the base 10. So we substitute this, we are going to get minus 20 log of base 10 mod of G of S H of S at omega PC. So what is the meaning of this one? This value is equal to infinity. Infinity means nothing, but suppose if it is 0, this is infinity. Then again, this value is totally infinity. Suppose this mod of G of H of S at omega PC, if I am going to assume its value is equal to, suppose let me assume its value is equal to infinity. Then what we are going to get, the overall value we are going to get is infinity, right? So therefore we can say this value we are going to get infinity. So overall value is also equal to infinity. So therefore we can say that finally, if the Nyquist plot of the G of H of S, if it does not intersect the negative real axis, then the gain margin in dB is nothing but infinity. Then the next point is, the variation in gain of the system does not alter the phase angle plot in the Bode plot diagram. The variation in the gain of the system does not alter the phase angle plot in the Bode plot diagram. See, whenever you are going to vary the gain of the system, then the magnitude plot is going to get changes, but not the phase angle plot, because in the magnitude we need to consider the magnitude of each and every part. Whereas in the phase angle we are going to consider only the phase angle part, but not the for a gain the phase angle is 0, so it is not going to take it inside. So therefore we can say by varying the gain of the system, only the magnitude plot is going to shift either upward or downward. Whereas by varying the gain of the system, the Bode plot is not going to get affected. So these point always you have to keep in the mind. So therefore, finally, I can say that by varying the gain of the system, the magnitude plot is not going to get changes, but only the Bode plot is going to get changes. So these point always you have to keep in your mind. So by varying the gain of the system, the magnitude plot is going to get changes, but not the phase angle part in the Bode diagram. So finally, I can say by varying the gain of the system, the magnitude plot is going to get altered, but the phase angle plot is not going to get altered in the Bode diagram. So then the next point is, the phase margin of the system is affected by the variation in the gain of the system. The phase margin of the system is affected by the variation in the gain of the system. So what is the phase margin formula? Phase margin is equal to 180 degree plus phase angle of G of S H of S at omega GC. So this is called as a phase margin formula. So you can see omega GC. Omega GC means it is a frequency at which the phase angle at which the magnitude of the G of H of S is equal to 1. So definitely the magnitude plot we are going to consider the gain value. So as the gain changes, omega GC changes. As omega GC changes, this value is going to get changes. So if this value changes, then overall value is also going to get changes. So we can say as the value of gain K increases, omega GC increases, so omega GC changes, so this value changes, so overall value is also going to get changes. So finally I can say whenever the gain of the system changes, the gain crossover frequency changes, the phase angle of G of S H of S changes, so therefore the phase margin is also going to get changes. So we can say the phase margin of the system is affected by the variation in the gain of the system. The next point is large response, peak in frequency response corresponds to a large overshoot in a transient response. And all systems which exhibit overshoot in a transient response may not exhibit the resonance peak in the frequency domain. For example, large response peak in frequency response corresponds to a large overshoot in a transient response. And all systems which exhibit the overshoot in the transient response may not exhibit resonance peak in the frequency domain. So what I am trying to tell you here basically, listen carefully. Suppose in the frequency domain, suppose if you are going to get a resonant peak, then by default we can say in the transient response with respect to time, the output, here we are going to have some peak value also we are going to get like this, but not vice versa. So this is a frequency domain, this is a time domain. So you can see clearly here, you can see, always you can see clearly, suppose in the frequency domain, if you are going to have some resonant peak, then in the time domain, you are going to have the peak value, but not the vice versa. Suppose if you are having a peak value in the time domain, it is not necessary to have a resonant peak in the frequency domain. So only in this direction it is true, but not in the vice versa. So we can say large response peak in frequency response. Large response peak in frequency response corresponds to a large overshoot in the transient response. And all systems which exhibit the overshoot in the transient response may not exhibit the resonant peak in the frequency domain. So this one always you have to keep in your mind. Suppose in the frequency domain, if you are having a resonant peak, then by default we can say yes, there is a peak in the transient response also in the time domain. But vice versa is not true. If any signal which is having a suppose if any signal but not the vice versa is true. If this is true means compulsory this is true, but if this is true means this is not compulsory true. So only I can say only in the frequency domain if you are having a resonant peak, then it can confirm that there is a peak in the transient in the time domain, but not the vice versa. So this one let me explain this one somewhat detail. Suppose if zeta is lesser than 0.707, then I can say the resonant peak value is greater than 1, whereas m peak in the transient in the response also you are going to get. Whereas whenever the zeta value is lying from 0.707 to 1, then the resonant peak won't exist, but the m peak is present in the transient response. So what I am trying to tell you, whenever the zeta value is less than 0.707, then there is a resonant peak. There is also peak overshoot in the transient response. Whereas whenever zeta value lies from 0.707 to 1, then there is no we can say the resonant peak is not there. When the resonant peak is not there, but there is a peak overshoot in the transient response. So you can say that finally I can say that only one thing, which is I can only say one thing, which is suppose if there is a resonant peak, then by default we are going to have a peak value in the transient response. But if you are having a peak in the transient response, it does not guarantee that there is a resonant peak also. So we can say that finally that whenever there is a resonant peak, it guarantees there is a peak overshoot in the transient response. But if there is a peak overshoot in the transient response, it does not guarantee that there is a peak value, there is a resonant peak value in the frequency response. So this one always you have to keep in your mind. So finally I can say only one thing, which is whenever damping ratio is lesser than 0.707, yes, there is a resonant peak in the frequency response, and there is also a peak overshoot in the transient response. But if the value of zeta is lying from 0.707 to 1, then there is no resident peak in the frequency response, but there is a peak quotient in the transient response. This one always you have to keep in your mind. Now, the next point is cos theta is equal to sine of 90 plus theta. I have already told you basically what is the cos theta. Cos theta is equal to sine of 90 plus theta. See, the 90 plus theta means the second coordinate. The second coordinate sine and cosec are positive. So therefore, now sine is a positive, so take here positive. Here 90 means whenever there is a 90 and 270, sine means to cos. If there is a 180 and 360, then sine means to sine itself. So therefore here there is a 90 means sine means to cos. This means cos theta. So because this one always you have to keep in mind, which is cos theta is equal to sine of 90 plus theta. The next point is, if the polar plot of g of s h of s is not enclosed in the -1 plus j0, then g of s h of s is stable, means no pole of g of s h of s is in the RHS of s plane. So listen carefully. If the polar plot of g of s h of s is not enclosed in the -1 plus j0, then g of s h of s is said to be stable. It means that no pole of g of s h of s is going to lie in the RHS of s plane. So simply, I can say, in simple words like this. In simple words, I can say like this. Suppose, if you are going to plot the polar plot of the g of s h of s, and then if it is not going to enclose the -1 plus j0, then it indicates that g of s h of s it is said to be a stable function, stable system. It means that no pole of g of s h of s is going to lie in the RHS of s plane. So these one always you have to keep in your mind. So whenever you are going to draw the polar plot of the open loop transfer function and it is not going to enclose the -1 plus j0, then we can say the system is said to be stable. Which one? Which is open loop transfer function is said to be stable. So no pole of the g of h of s is going to lie in the RHS of s plane. So this one always you have to keep in your mind. So finally I can say, whenever you are going to draw the polar plot of the open loop transfer function g of h of s, if it is not going to enclose the -1 plus j0, then the open loop transfer function is said to be a stable function. It means that no pole of the g of h of s is going to lie in the RHS of s plane. So this one always you have to keep in your mind. The next point is, always figure out the n from the Nyquist plot. So always try to figure out the n from the Nyquist plot. What is the value of n? I have already told you n is equal to p1 is z, where n is the number of encirclements in the g of h of s plane from the point -1 comma j0. Take it positive for anticlockwise and take it negative for clockwise. Then p indicates number of poles of the g of h of s which are going to present to the right of s plane, and it indicates the number of closed loop poles which are going to lie in the RHS of s plane. So this one always I already told you. So n is equal to p minus z. P value we are going to get from the open loop transfer function. Z value we are going to get from the Raoult Searles criteria. Then the n value we are going to get by this equation is equal to p minus z. So therefore, p value we are going to get from the open loop transfer function. Z value we are going to get from the Raoult Searles criteria, and n value we are going to get from this equation is equal to p minus z. So this one always you have to keep in your mind. The next point is, higher the resonant peak, higher is the maximum overshoot of the step response. I already told you, higher the resonant peak, higher is the maximum overshoot of the step response. And I've already told you one important point. Whenever the zeta value is less than 0.707, then the resonant peak value is always greater than 1. It is always equal to greater. It is always greater than 1. And the peak quotient is also going to exist. Whereas, whenever the zeta is greater than 0.07, then the resonant peak is nothing but it is equal to 1. Its value is equal to 1. But the resonant peak is always the resonant peak value its value is equal to 1. Whereas the peak quotient value is going to be present. So this one I have already told you here. So therefore, you can see clearly. So basically we can say 1 means it won't exist. It won't exist, we can say. It won't exist because its value is equal to 1. So therefore we can say that basically we can say that whenever zeta value is less than 0.707, then the resonant peak value is going to exist and the peak quotient is also going to exist. But zeta value is greater than 0.707, the resonant peak won't even exist, but the peak quotient is going to exist. As the resonant peak increases, the peak which is also going to get increases on the step response. So higher the resistance peak, higher is the maximum overshoot of the step response. The next point is, for the minimum phase system to be stable, both gain margin and the phase margin should be positive. So already told you what is the minimum phase system. Minimum phase system means all the poles and zeros if they are going to line the list of S1, then we say it is a minimum phase system. If at least any of the zero it is lying in the rest of S1, then we say it is a non-minimum phase system. So we can say that whenever a minimum phase system, so a minimum phase system is said to be stable when both the gain margin as well as the phase margin both are positive. So I've already told you one important point, which is for a stable system. For a stable system, the gain crossover frequency is lesser than phase crossover frequency, and both the gain margin and the phase margin both are positive. But for a marginally stable system, the gain crossover frequency is called phase crossover frequency, and both the gain margin and phase margin both are equal and its value is equal to 0. But whenever the gain crossover frequency is greater than phase crossover frequency, we say the system is said to be unstable system, and both the gain margin as well as phase margin both are said to be negative. So these one I have already told you so many number of times. The next one is the phase margin, gain margin, bandwidth or frequency domain specifications, whereas the maximum overshoot is the time domain specification. So phase margin, gain margin and bandwidth, these are basically the frequency domain specifications. So this phase margin, gain margin and bandwidth. Bandwidth I have already told you. I have drawn the frequency response and I have also given the formula for bandwidth. Gain margin also I have already told you. It is basically regarding to the frequency. And the phase margin is also dependent upon the gain crossover frequency. So all these are the frequency domain specifications. Whereas the peak overshoot, which is LP is equal to the power of minus zeta pi by I root over 1 zeta square. This is the time domain expression. So you can say finally, phase margin, gain margin, bandwidth. These are the frequency domain specifications, while the maximum overshoot is a time domain specification. So finally, I can say gain margin, phase margin, and bandwidth. These are the frequency domain specifications, while the maximum overshoot is the time domain specification. So finally, I can say the phase margin, the gain margin, and bandwidth. These are the frequency domain specifications, while the maximum overshoot is the time domain specification. So finally, I can say that the phase margin, gain margin, bandwidth, these are the frequency domain specifications, while the maximum overshoot is the time domain specification. So this one always you have to keep in your mind. So finally, I can say the phase margin, gain margin, and the bandwidth, these are the frequency domain specifications, whereas the maximum overshoot is the time domain specification. So this one always you have to keep in your mind. The next point is, it is possible to have the open loop system as unstable and the closed loop system is stable. So it is possible to have an open loop system as unstable and the closed loop system is stable. So basically here, what they are saying is, I have already told you, open loop system and the closed loop system. So see, I have already told you this point so many number of times, but let me repeat so that you can easily able to understand. Suppose it is possible to have open loop system as unstable system, and the closed loop system can be stable, or it can also be unstable. Suppose if this is stable, it can be stable or it can be unstable also. So I already told this one. Suppose if the open loop system is unstable, then the closed loop system can be either stable or it can be unstable also. If the open loop system is stable, then the closed loop system can be either stable or unstable. So this one always indicate in the plan. So whenever the open loop system is stable, the closed loop system can be either stable or unstable. If the open loop system is unstable, then the closed loop system can be either stable or unstable. So this one always you have to keep in your mind. So it is possible to have a open loop system as unstable and a closed loop system as stable. So this one always you have to keep in your mind. The next point is, for a parallel resonance circuit, the relation between the omega d, omega n and bandwidth is omega d is equal to under root over omega n square minus bandwidth by 2 whole square. So this formula always you have to keep in your mind. So omega d is equal to under root over omega n square minus bandwidth by 2 whole square. So this formula always you have to keep in your mind. So for a parallel resonance circuit, the relation between the omega d, omega n and the bandwidth, omega d is equal to under root over omega n square minus bandwidth by 2 whole square. So this formula always you have to keep in your mind. So we can say for a parallel resonance circuit, the relation between the omega d, omega n and bandwidth, which is equal to omega d is equal to under root over omega n square minus bandwidth by 2 whole square. So this formula always you have to keep in your mind. So in the case of parallel resonance circuit, the relation between the omega d, omega n and bandwidth. Omega d means damping frequency plus omega n is equal to natural frequency and BW means bandwidth. Omega d is equal to under root over omega n square minus bandwidth by 2 whole square. So this formula always you have to keep in your mind. So omega d is equal to omega n square under root over omega n square minus bandwidth by 2 whole square. The next point is, you know, G of s, H of s is equal to, it is a ratio of the numerator over the denominator. So here, basically, denominator is complex number. It has some real part and the imaginary part. So the imaginary part, this part is equal to 0 and we can figure out the omega PC. Basically, here, you can see clearly, I already told you, see, what is the meaning of phase pause or frequency? Phase pause or frequency is the frequency at which the phase angle of G of s, H of s is equal to minus 180 degree. Either you can go by like that is the actual method. But here also, suppose if you equate this part to 0, then what is going to happen? If this part is equal to 0, then definitely you are going to get some real part only. So by that also, you can say, same thing you are going to get. Even by the option I have already told you that at omega PC is nothing but basically I have already told you, it is a frequency at which, so basically here, this part is equal to 0 and we can figure out the omega PC. So this part always you have to keep in your mind. So therefore we can say, simply, I have already told you, suppose here we have substitute. So here we have substitute. In the G of s, H of s, I have substitute. S is equal to J omega PC. I have substitute. And I got some, like this one I have got. And if we equate this part to 0, we are going to get the value of the omega PC. And I have already told you omega PC means it's the frequency at which the phase angle of G of s, H of s is equal to minus 180 degree. So by that also you can get the value of the phase crossover frequency. Either by this one also you can get the phase crossover frequency. So in the case of G of H of s, substitute S is equal to J omega PC. So you are going to get some equation like this and equate the imaginary part downward, equal to 0 and you are going to get the value of the omega PC. So this part always you have to keep in your mind. So therefore we can say finally, for the open transfer function G of H of s, if you substitute S is equal to J omega PC, you are going to get like this. And for denominator, if you equal the imaginary part to 0, then we are going to get the value of the omega PC. But even though you can get by another method also, which is the phase angle of the G of s, H of s at omega PC is equal to minus 180. Even by that method also you are going to get the value of the omega PC. In both the ways you are going to get the same thing. The next point is that if the polar plot of G of H of s does not cut the negative real axis, then the gain margin is said to be infinity dB. It means the closed loop poles always lie in the ellipsis of S plane for 0 less than or equal to k less than or equal to infinity. Listen carefully. If the polar plot of G of H of s does not going to intersect the negative x-axis, then the gain margin is said to be infinity dB. It means the closed loop poles are going to always lie in the ellipsis of S plane for all ranges of the k. So we can say simply, whenever the polar plot of the G of H of s, if it does not going to cut the negative axis, then the gain margin is said to be infinity dB, and it means the closed loop poles are always going to lie in the ellipsis of S plane for all values of the range of the k. So we can say that if the polar plot of the G of s, H of s, if it does not going to cut the negative x-axis, then the gain margin is said to be infinity dB. It means that the closed loop poles are always going to lie in the ellipsis of S plane for all value of the range of the k. So finally I can say, if the polar plot of G of H of s does not going to cut the negative real axis, then we can say gain margin is said to be infinity dB. It means that the closed loop poles are always going to lie in the ellipsis of the S plane for all the range of values of the k. The next point is, the polar plot has the limitations for portraying the frequency response of a system because The calculations of the frequency response is tedious and does not indicate effect of individual poles and zeros. The polar plot has limitations for portraying the frequency response of a system because the calculations of frequency response is tedious and does not indicate the effect of the individual poles and the zeros. So here they are saying that the polar plot has limitations for portraying the frequency response of a system. Basically, they are saying that the polar plot has basically some limitations for portraying the frequency response of a system because the calculations of the frequency response is tedious and does not indicate effect of the individual poles and zeros. So they are saying that this polar plot has basically some limitations for portraying the frequency response of the system because the calculations are very low. The frequency calculations are very high and it is very tedious and it is even does not going to indicate the effect of the individual poles and the zeros. So this basically the polar plot has some limitations for portraying the frequency response of the system because the calculations of the frequency response is very tedious and also it does not going to indicate the effect of the individual poles and zeros. So finally I can say the polar plot has some limitations for portraying the frequency response of a system because the calculations of the frequency response is very tedious and it does not going to indicate the effect of the individual poles and zeros. So we can say the polar plot has basically some limitations for portraying the frequency response of a system because the calculations of the frequency response is very tedious and does not going to indicate the effect of the individual poles and zeros. Means it is not going to show the individual effect of the poles and zeros. So it is not going to show the effect of the individual poles and zeros. Means overall it can show but not individual. So finally I can say the polar plot has some limitations for portraying the frequency response of a system because the calculations of the frequency response is very tedious and it does not going to indicate the effect of the individual poles and zeros. The next point is the cutoff rate indicates the ability of the system to distinguish the signal from the noise. The cutoff rate indicates the ability of the system to distinguish the signal from the noise. So basically, with the help of cutoff only, we can distinguish which is the noise and which is the signal. See, if anything which is above the cutoff, we say it is an actual signal, and if anything is below the cutoff, we are not going to take it. It's like suppose, let me assume, suppose there is some, we can say, low pass filter. So this is a cutoff frequency. So below these things, it is going to pass every frequency, but above this, any signals having a frequency above this one, the system will never respond to that. So this is called the cutoff frequency. So cutoff frequency or cutoff rate is going to distinguish the actual signal as well as the noise signal. The cutoff rate is going to indicate the ability of the system to distinguish the signal from the noise. So we can say the cutoff rate is going to indicate the ability of the system to distinguish the signal from the noise. So cutoff rate is going to distinguish which is the actual signal and which is the noise signal. So finally I can say the cutoff rate is going to indicate the ability of the system to distinguish the signal from the noise. The next point is resonant frequency is indicative of the speed of the transient response. Resonant frequency is the indicative of the speed of the transient response. So resonant frequency formula, what is the resonant frequency? Omega or resonant frequency is equal to omega n into under root over 1 minus 2 zeta square. So this is called the resonant frequency. So this resonant frequency is going to indicate, it is an indicator of the speed of the transient response. So this resonant frequency is basically going to indicate the speed of the transient response. So this resonant frequency is going to indicate the speed of the transient response. Resonant frequency formula omega is equal to omega n into under root over 1 minus 2 zeta square. So finally I can say this resonant frequency is basically it is an indicator of the speed of the transient response. The next point is gain margin is the factor by which the gain of the system should be increased in order to drive into the verge of the instability. So gain margin is the factor by which the gain of the system should be increased to drive to the verge of the instability. So basically we can say what is the meaning of gain margin? Suppose if you have a gain margin as positive, then we need to increase the gain of the system by this much factor in order to make the system to be unstable. So we can say this is the stable region and this is the unstable region. So gain margin is positive, means we can say the system is said to be stable or stable. So if gain margin is positive, suppose if you are going to increase the gain of the system by this much amount of gain margin, then definitely we are making the system to become unstable. So it is in the, suppose if you are increasing this much amount of factor, then it is basically in the verge of the instability. So it is going to become unstable. So therefore we can say gain margin is the factor by which the gain of the system should be increased in order to drive into the verge of instability. Similarly, the phase margin also. Phase margin means this much amount of angle you should increase in order to make the system to become unstable. So gain margin is a factor by which the gain of the system should be increased in order to drive it into the verge of the instability. So we can say the gain margin is a factor by which the gain of the system should be increased in order to drive into the verge of the instability. So finally I can say gain margin is the factor by which the gain of the system should be increased in order to drive into the verge of the instability. So finally I can say gain margin is the factor by which the gain of the system should be increased in order to drive into the verge of the instability. So I've already told you, whenever the gain crossover frequency is less than phase crossover frequency, the system is said to be stable, and also both the gain margin and phase margin both are positive. And for unstable system, the gain crossover for the marginally stable system, the gain crossover frequency is equal to phase crossover frequency, whereas the gain margin and phase margin both are equal to 0. Whereas whenever the gain crossover frequency is greater than phase crossover frequency, the system is said to be unstable, and also we can say that the gain margin and phase margin both are said to be negative. So this point also I have already told you. So finally I can say gain margin is a factor by which the gain of the system should be increased in order to drive into the verge of the instability. The next point is Nicholas chart is used to determine the closed loop frequency response. Nicholas chart is used to determine the closed loop frequency response. So we can say Nicholas chart is basically used to determine the closed loop frequency response. Whereas the polar plot is for the open loop transfer function, whereas the Nicholas chart is for the closed loop frequency response. So Nicholas chart is basically used to determine the closed loop frequency response. And in the Nicholas chart, there is nothing like 0 dB loop. So these two things always indicate in mind. So Nicholas chart is basically used to determine the closed loop frequency response, and there is nothing like 0 dB loop in the case of Nicholas chart. So we can say Nicholas chart is basically used to determine the closed loop frequency response, and there is nothing like 0 dB loop in the case of Nicholas chart. So finally I can say Nicholas chart is basically used to determine the closed loop frequency response, and there is nothing like 0 dB loop in the case of the Nicholas chart. So we can say finally that the Nicholas chart is basically used to determine the closed loop frequency response, and there is nothing like 0 dB loop in the case of the Nicholas chart. So finally I can say Nicholas chart is basically used to determine the closed loop frequency response, and there is nothing like 0 dB loop in the case of the Nicholas chart. So finally I can say Nicholas chart is basically used to determine the closed loop frequency response, and there is nothing like 0 dB loop in the case of Nicholas chart. So finally I can say Nicholas chart is basically used to determine the closed loop frequency response, and there is nothing like 0 dB loop in the case of Nicholas chart. So these points always you have to keep in your mind. Now the next points are a lead compensator is going to improve the transient characteristics, means it is going to change the zeta as well as the omega here. So basically how to remember this one? See, basically lead compensator is going to improve the transient characteristics of the system. I've already told you. So lead has more volts, so transient has more volts, so we can easily match them. So lead compensator is going to improve the transient characteristics of the system. So what are the transient characteristic parameters? Zeta as well as the omega n. So therefore, what is the transient characteristics parameters? Zeta and omega n. So whenever the response is going to get changes, then definitely zeta is going to get changes, and the omega n is also going to get changes. So therefore we can say both the zeta as well as the omega n both are going to get affected. So transient characteristics means the transient response. The transient response. This is called transient characteristics. So as zeta changes, the nature of this transient response is also going to get changes. As the omega changes, the nature of the transient response is also going to get changes. So therefore, we can say finally, lead compressor is going to improve the transient characteristics of the system. So therefore, both the zeta as well as omega both are going to get affected because zeta and omega, these are the parameters which are basically associated with the transient performance analysis. So therefore, whenever the transient response is going to get changes, zeta as well as the omega both are going to get affected. Lag capacitor does not improve the transient characteristics, means no effect on zeta and omega. So I already told you, lag capacitor is basically used to improve only the steady state characteristics of the system. So therefore, we can say it is not going to affect the transient characteristics. So therefore, we can say there is no effect on the zeta and the omega n. So this one always you have to keep in your mind. So I can say simple words that lag capacitor is basically used to improve the steady state characteristics of the system. So it is not going to improve the transient characteristics. So therefore, there is no effect on the zeta and omega n, as zeta and omega n are the transient characteristics performance parameters. So finally, I can say lead capacitor is going to improve the transient characteristics of the system. So therefore, zeta and omega n are the parameters which are associated with the transient characteristics. So they are going to get affected. As the lag capacitor, it is going to improve only the steady state characteristics of the system. So there is no effect on the transient characteristics. So there is no effect on the zeta and omega n. So whenever the zeta changes and omega n changes, the nature of the transient response is going to get varied. The next point is, no capacitor has the pole of zero in the arches of S plane. Simple concept here. See, no matter what are the capacitor we take, whether the lead capacitor, whether the lag capacitor, whether the lag lead capacitor, always their poles and zeros always are going to present only in the LHS of S plane. So there is no capacitor has a pole of zero in the arches of S plane. So each and every capacitor that we have discussed, all their poles and zeros are present only in the LHS of S plane. So I've already told you, all the capacitors that we have discussed, they have their poles and zeros only in the LHS of S plane. So there is nothing like capacitor. So we say, suppose if there is a pole or zero which is present in the right of S plane, then we say it is not a capacitor. It is not a compensator. If any pole of zero, if it is going to present in the right of S plane, then we say that is not a compensator transfer function, pole zero plot. So no capacitor has a pole of zero in the right of S plane. The next point is, Pi won't improve the transient characteristics, means there is no effect on zeta and omega n. As I have already told you, Pi is nothing but proportional integrator. Simply we can say it is a lag compensator. So lag compensator is basically used to improve only the steady state characteristics of the system. So there is no effect on the transient state characteristics. So therefore there is no effect on the zeta and omega n, because zeta and omega n are the parameters which are related to transient characteristics itself. The next point is, phase theory compensator is going to improve the gain crossover frequency as well as the bandwidth. I have already told you this important point so many number of times. So phase theory compensator is going to improve the gain crossover frequency as well as the bandwidth of the system. Improving this, basically both are going to get increases. So both are going to get increases. The gain crossover frequency increases as well as the bandwidth also increases in the case of phase theory compensator, because in the case of phase theory compensator, it is going to improve the transient characteristics of the system. So whenever the transient characteristics are going to get improved, means we can say the rise time is going to get decreases and the bandwidth is going to get increases, because the plot is always equal to constant, and the damping ratio is also going to get increases. And the damping ratio increases, then what is going to happen? The maximum peak quotient is also going to get decreases. It is going to get decreases. And these are the things always you have to keep in mind, and omega n is also going to get affected. This one I already told you. So now you can see clearly, in a given transfer function, cancel the common terms and then decide whether it is a lead compensator or the lag compensator. Suppose if they are given some complex transfer function, try to make it into factors and delete the common factors and the common terms, and then whatever you're going to get the new one based on this, try to figure out whether it is a real compensator or flat compensator. So basically, they are going to give a very complex transfer function, try to factorize it and remove the common terms and then decide whether it is a lead compensator or the lag compensator. And I've already told you, in the case of phase shift compensator, as I've already told you, the price time is going to get decreases, bandwidth is going to get increases, delay is going to get increases, maximum frequency is going to get decreases, and the gain transfer frequency is also going to get increases. Just now I already told you. So therefore, finally I can say, phase shift compensator means it is a compensator in which we have a 0 is more closer to origin compared to 4. The output is always going to lead the inputs. And also, it is going to improve only the Canyon catastrophe system. So because of this, the rise time is going to get decreases. So bandwidth is going to get increases. Timing ratio is going to get increases. So peak, maximum frequency is going to get decreases. And the gain crossover frequency is also going to get increases. And there is also change in the actual frequency omega gain. So these things always you have to keep in your mind. The next point is, the smallest set of variables which determine the state of dynamic system are called as the state variables. The smallest set of variables which are going to determine the state of the dynamic system are called as the state variables. The smallest set of variables which are going to determine the state of the dynamic system are called as the state variables. So we can say the smallest set of variables which are going to determine the state of the dynamic system are called as the state variables. The smallest set of variables which are going to determine the state of the dynamic system are called as the state variables. So always remember, the smallest set of variables which are going to determine the state of the dynamic system, which are basically called as the state variables. The smallest set of variables which are going to determine the dynamic state of the system, which are called as the state variables. The smallest set of variables which are going to determine the state of the dynamic system, which are called as the state variables. So finally I can say, the smallest set of variables which are going to determine the state of the dynamic system, which are basically called as the state variables. The smallest set of variables which are going to determine the state of the dynamic system, which are called as the state variables. So finally I can say, the smallest set of variables which are going to determine the state of the dynamic system, which are called as the state variables. So finally I can say, the smallest set of variables which are going to determine the state of the dynamic system are called as the state variables. The smallest set of variables which are going to determine the state of the dynamic system are called as the state variables. So finally I can say, the smallest set of variables which are going to determine the state of the dynamic system, which are called as the state variables. So finally I can say, the smallest set of variables which are going to determine the state of the dynamic system, which are called as the state variables. The next point is, controllability is basically used to control the state variables, whereas observability is basically used to measure the state variables. So this point always you have to keep in your mind. C means controllability is basically used to control the state variables, whereas observability is basically used to measure the state variables. So this point always you have to keep in your mind. So we can say that controllability is basically used to control the state variables, whereas the observability is basically used to measure the state variables. So finally I can say, controllability is basically used to control the state variables, whereas the observability is basically used to measure the state variables. So finally I can say, controllability is basically used to control the state variables, whereas the observability is basically used to measure the state variables. So these points always you have to keep in your mind. So controllability is basically it is used to control the state variables, whereas the observability is basically it is used to measure the state variables. So this point always you have to keep in your mind. So finally I can say, controllability is basically it is used to control the state variables, whereas the observability is basically it is used to measure the state variables. So finally I can say, controllability is basically it is used to control the state variables, whereas the observability is basically used to observe the it is basically used to measure the state variables. So finally I can say, controllability is basically it is used to control the state variables, whereas the observability is basically used to measure the state variables. So now the next one is, suppose there is a block diagram like this. So 1/s means this is basically integrated in the Laplace domain. So this is the x1 is x1 dot, integration of x1 dot is nothing but x1 we are going to get. So this is x means x1 dot. So integration of input is nothing but output. It's the integration. So output is the integration of the input. So integration of x1 dot is nothing but x1. So this is a scalar multiple k. So if this is a negative feedback, so if you apply j of s is 1 by s and h of s is a, so therefore we are going to get this one j of s by 1 plus j of s h of s. So in simplify we are going to get and then multiply by k, we are going to get, this is the format we are going to get, is k by s plus a. So this block diagram we can write like this, which is a negative feedback. This is 1 by s, this is a, and this is k. So these both are equal. So we can say both are equal. This is x1, this is x1 dot. So x1 is the state variable. So I wanted to output of any integrator, current in an inductor, and a voltage is a capacitor. These are said to be state variables. I wanted to show output of the integrator and the current in an inductor and the voltage is a capacitor. These are said to be basically, we can say, the state variables. So I already told you this important point. The next point is nature of the eigenvalue. So nature of the eigenvalue and the nature of the singular point. So we are going to discuss the next point is the nature of the eigenvalue and the nature of the singular point. So for a complex conjugate pair, we are going to get the focus point. For a pure imaginary pair, we are going to get the center. And for real and equal but with opposite sign, we are going to get the saddle point. And for real, distinct and negative, we say these are said to be stable point. Listen carefully. For a real, distinct and negative, what is the meaning of this one? So real, distinct and negative means we can say the stable point means all the things are going to lie in the rest of its plane with the real. So complex conjugate pair means we can say there is a sigma and there is a omega. Real part and the imaginary part. Then we can say it is a focus point. Purely imaginary pair means simply center. And for real equal, what is the opposite sign means one is on the x-axis and the other in the r-axis, but purely on the x-axis. Then we say it is a saddle point. For real, distinct and negative, we say it is a stable point. So finally listen carefully. For the nature of the eigenvalue and the nature of the singular point, which is for a complex conjugate pair, we are going to get the focus point. And for pure imaginary pair, we are going to get the center. And for real and equal, but with opposite side, we are going to get the saddle point. And for real, distinct and negative, we are going to get the stable point. So listen carefully. For a complex conjugate pair, we are going to get the focus point. And for pure imaginary pair, we are going to get the center. And for real and equal, but with opposite side, we are going to get the saddle point. And for real, distinct and negative, we are going to get the stable point. So finally I can say nature of the eigenvalue and nature of the singular point. For a complex conjugate pair, we are going to get the focus point. And for a pure imaginary pair, we are going to get the center. And for real and equal, but with opposite side, we are going to get the saddle point. And for real, distinct and negative, we are going to get the stable point. So these things always you have to keep in your point. So finally I can say the nature of the eigenvalue and the nature of the singular point. For a complex conjugate pair means there is a real part and an imaginary part, then we are going to get the focus point. For a pure imaginary pair means there is no real part, only there is an imaginary part, then we are going to get the center. And for real and equal but with the opposite side means all are going to lie in the real axis and they are equal we have to put of opposite side, then we are going to get the saddle point. For real, distinct and negative, then we are going to get the stable point. Yes, all are going to lie in the rest of the sphere. Then we can, this one is said to be stable point. Eigenvalues means simply we can say eigenvalues means because the two unit poles or the roots of the characteristic equation 1 plus 3 of each of is equal to 0. The next point is the transfer function of a control system does not have pole zero cancellation, then system is compulsory, controllable as well as observable. So if the transfer function of a control system does not have the pole zero cancellation, then the system is compulsory, controllable as well as observable. Suppose if you take a transfer function and if there is nothing like pole zero cancellation takes place only when there is a common root. When there is a common root, yes, then only there is a pole zero cancellation. Suppose if there is no cancellation means we can say it is compulsory, controllable as well as observable. I already told you what is the meaning of controllable. Controllable means basically to control the state variables Observable means basically to measure the state variables. This point I've already told, so therefore we can say finally, that the transfer function of a control system that is not having homogeneous cancellation, the system is compulsory controllable as well as observable. So finally I can say if the transfer function of a control system does not have homogeneous cancellation, then system is compulsory controllable as well as observable. So finally I can say for a given transfer function of a control system, if there is nothing like homogeneous cancellation, then we can say the system is compulsory controllable as well as observable. So finally I can say that for a given transfer function of a control system, if it is not having any homogeneous cancellation, then default the system is said to be compulsory controllable as well as observable. The next point is, in discrete system, the characteristic equation is the modulus of Zi minus A is equal to 0. See, in the case of continuous time system, what is the characteristic equation? Which is the determinant of Si minus A is equal to 0. This is in the case of the continuous time, and this is in the case of the discrete time. So, in the continuous time, the characteristic equation is the determinant of Si minus A is equal to 0, whereas in the discrete time, the characteristic equation is the determinant of Zi minus A is equal to 0. So finally I can say, in the case of continuous time system, the characteristic equation is the determinant of Si minus A is equal to 0. Whereas in the case of discrete time system, the characteristic equation is the determinant of Zi minus A is equal to 0. So finally, I can say that in the case of discrete time system, the characteristic equation is the determinant of Zi minus A is equal to 0. Whereas in the case of continuous time system, the characteristic equation is the determinant of Si minus A is equal to 0. So finally, I can say like this. So finally, I can say in the case of continuous time system, the characteristic equation is the determinant of Si minus A is equal to 0. Whereas in the case of discrete time system, the characteristic equation is the determinant of Zi minus A is equal to 0. The next point is the peculiar characteristics of nonlinear system are the peculiar characteristics of the nonlinear system are. First, we are going to discuss some characteristics of the nonlinear system. I have already told you nonlinear system means the system is not going to satisfy the superposition theorem as well as homogeneous principle. That is called as the nonlinear system. So if any system is not going to satisfy the superposition theorem as well as the homogeneity principle, that is called the nonlinear system. So now we'll discuss some points regarding this one. If the input is a sine wave of radial frequency omega, the output is generally non-sinusoidal containing frequencies which are multiple of omega. So for linear system, if the input signal is having a frequency omega, then the output is also having the same frequency omega. But in the case of nonlinear system, here, if the input having a signal frequency omega, then the output will have lot of frequencies like omega 2, omega 3, omega, and goes on. The next point is the jump response may occur. Means there is a jump response. It will not have it will have basically sudden changes. In the output, you can see sudden changes in the case of nonlinear systems. The system exhibits the self-sustained oscillations of fixed frequency and amplitude. The system is going to exhibit the self-sustained oscillations of fixed frequency as well as amplitude. And the response to a particular phase signal may not be a guide to the behavior to the other inputs. The response to a particular phase signal may not be a guide to the behavior to the other inputs. So in the case of LTI system, if you apply the h of t, then you are going to get the h of t. So with the help of h of t, for any input we can figure out the output. But in the case of nonlinear systems, we can't tell like that. It is going to get varied. So even though you know the h of t, for any input you can't figure out the output for the nonlinear systems. So these are the important characteristics of the nonlinear systems. So we can say, in simple words, I can say like this. Even though input is having a frequency omega, the output signal frequency can be omega and can be multiple of omega also. And there is also jump response, sudden change in output also we can see. And the system is going to exhibit the self-sustained oscillations of fixed frequency as well as the amplitude. And the response to a particular signal may not be a guide to the behavior to the other inputs. So finally I can say The peculiar characteristics of the nonlinear system are: if the input is a sine wave of varying frequency omega, the output is generally non-sinusoidal containing frequencies which are multiple of omega. The jump response may also occur. The system is going to exhibit the self-sustained oscillations of fixed frequency and amplitude. The response to a particular phase signal may not be a guide to the behavior to the other inputs. So we can say finally the important characteristics of the nonlinear system are: the input is a sine wave of hidden frequency omega, then the output is generally non-sinusoidal continuous frequencies which are multiple of omega. The jump response also may occur. The system is going to exhibit the self-sustained oscillations of fixed frequency and amplitude. The response to a particular phase signal may not be guide to the behavior to the other inputs. So in simple words, I can say finally, suppose the important characteristics of the nonlinear system are: suppose if the input is having a frequency omega and the output can have the frequencies of multiple of omega, which is omega, 2 omega, 3 omega, 4 omega, and so on. But for LTI system, if the input is having the frequency omega and output is also having the same frequency omega, the jump response may also occur. Means we can say there is a sudden changes in the output in the case of nonlinear system, or not in the case of conventional, in the case of linear systems. And also in the case of nonlinear system, the system is going to exhibit the self-sustained oscillations of fixed frequency and amplitude. And also we can say in the case of LTI system, for given input delta of t, if we get the h of t, delta of h of t, for any input we can figure out the output. But in the case of nonlinear systems, even though if we get delta of t, we got h of t, but with delta of h of t, for any input we can't figure out the output. The output is going to be vary. So this is all about this important characteristics of the nonlinear system. The next point is, for radar tracking systems, signals are available in the form of pulse trains, because the stability of a discrete time system is decreased as the sampling period is shortened. So we can say stability. Stability is basically directly proportional to pulse width. Pulse width. PW means pulse width. As the pulse width decreases, the stability is also going to decrease. As the pulse width increases, the stability is also going to get increased. So we can say for radar tracking system, signals are available in the form of pulse trains, because the stability of a discrete time system is decreased as the sampling period is shortened. So as the sampling period decreases, the stability is also going to get decreases. So this point always you have to keep in your mind. So therefore we can say as the sampling period decreases, the stability is also going to get decreases. As the sampling period increases, the stability also increases in the case of discrete domain. So for radar tracking system, signals are available in the form of pulse trains, because the stability of a discrete time system is decreased as the sampling period is shortened. So we can say finally, for radar tracking systems, signals are available in the form of pulse trains, because the stability of a discrete time system is decreased as the sampling period is shortened. So we can say the stability is always very proportional to pulse width. As the pulse width reduces, the stability is also going to get reduces. As the pulse width increases, the stability is also going to get increases. So therefore we can say finally, for radar tracking system, signals are available in the form of pulse trains, because the stability of a discrete time system is decreases as the sampling period is shortened. So finally I can say, for radar tracking system, signals are available in the form of pulse trains, because the stability of a discrete time system is decreases as the sampling period is shortened. So stability is always very proportional to pulse width. As the pulse width decreases, the stability is also going to decreases. So finally I can say, for a radar tracking systems, signals are available in the form of pulse trains, because the stability of a discrete time system is decreases as the sampling period is shortened. So finally I can say, for a radar tracking systems, signals are available in the form of pulse trains, because the stability of a discrete time system is decreases as the sampling period is decreases. Means the stability in the case of discrete time system is always very proportional to pulse width. As the pulse width reduces, the stability is also going to get reduces. As the pulse width increases, the stability is also increases in the case of the discrete time system. The next point is, a discrete time system is stable if all the roots of the characteristic equation lie within the circle of unit radius. We already told you, for a system to be stable in the continuous time domain, we can say that all the poles should lie in the S of S plane. So whenever all the LHS of H plane is going to plot inside the unit circle, whereas also points on the imaginary axis are going to plot on the unit circle, whereas all the points on the axis of the axis of the H plane are plotted to the outside of the unit circle. So this one I already told you. So in the case of a discrete time system to be stable, all the nodes of the constitutive equation they must lie within the unit circle itself. So we can say a discrete time system is stable if all the roots of the constitutive equation they lie within the circle of the unit radius. So I already told you how we are going to map the S plane and Z plane. So all the points of the LHS, all the LHS points on the S plane, they are going to map inside the unit circle, whereas all the points on the imaginary axis of S plane, they are mapped to the on the unit circle of Z plane, whereas all the points on the axis of the S plane, they are mapped to the outside the unit circle in the Z plane. So this point I have already told you. So the number of times, so therefore we can say for this system to be stable, all the roots of the constitutive equation they must lie within the unit circle itself. The next point is state model is not a unique, whereas the transfer function for the given system is unique. State model can be derived from the transfer function of the system. I have already told you we are going to compare the transfer function as well as the state model. In that case, I have already told you in the case of transfer function, we have assumed the initial conditions are 0. Whereas in the case of state model, we have considered the initial conditions. I have already told you the transfer function is a unique. The transfer function for a given system is unique, whereas the state model for a given system is not a unique one. I have already told you. And I have already told you how to derive the state model from the given transfer function also. I have already told you. So, and I have also told you the vice versa also. So if you know the state model, you can get the transfer function. If you know the transfer function, you can get the state model. So these two concepts I have already told you. So finally I can say, so whenever you are going to compare the transfer function and the state model, by deriving the transfer function, all the initial conditions are assumed to be 0. Whereas in the case of state model, all the initial conditions are NCR. Whereas the transfer function for a given system is unique, the stable model for a given system is unique one. And I have already told you how to, if you know the state model, how to figure out the transfer function. I have already told you, if you know the transfer function, how to get the state model. All these concepts already I have told you. The next point is, the state equations in a phase variable canonical form can be obtained from the transfer function by direct decomposition. The state equations in a phase variable canonical form can be obtained from the transfer function by direct decomposition. So, basically, the state equations in the phase variable canonical form can be obtained from the transfer function by direct decomposition. So, from the transfer function by direct decomposition, we can get back the state equations. So, from the transfer function by direct decomposition, we can get the state equations. So, we can say the state equations in the case of phase variable canonical form, we can easily obtain from the transfer function by direct decomposition. So, these concepts already I have told you. So, therefore, we can say the state equations in the case of phase variable canonical form, we can easily obtain from the transfer function by direct decomposition. The state equations in the phase variable canonical form, we can easily obtain from the transfer function by the direct decomposition. So we can say the state equations in the case of phase variable canonical form, we can easily obtain from the transfer function by direct decomposition. So finally, I can say the state equations in the case of phase variable canonical form, we can easily obtain from the transfer function by the direct decomposition. So finally, I can say the state equations in the case of phase variable canonical form, we can easily obtain from the transfer function by direct decomposition. The next point is, when a transfer function model is converted into state space model, the order of the system will never change always. So when a transfer function model is converted into state space model, the order of the system will never change always. So we can say whatever the order of the transfer function, say will be the order of the state space model also, it will never get changed. And I already told in the case of state space variable, the order of the number of state variables is equal to order of the system. I already told you. In the case of state space model, the number of state variables is equal to the order of the system. So order of the system will be same in the both the transfer function as well as the state space model. So in the case of transfer function model and in the case of state space model, the order of the system will be same as it is. Even though you are converting from transfer function model to state space model or state space model to transfer function model, in both the cases, the order of instance will be same. It will never get changes. The next point is free response is represented by the state transition matrix of the system. Free response is represented by the state transition matrix of the system. I have already told you, basically, free response means the input is equal to 0 and we are going to get the output based on the state variables. That is called as a free response. Free response means the input is equal to 0, but because of state variables only, we are going to get the, because of initial conditions only, we are going to get the output. That is called as the free response. And I have already given the expression also, I have already given in the previous class itself, in the formula class itself. So free response is represented by the state transition matrix of the system. The next point is sample data system requires whole circuit and whole circuit convert the signal into analog form. Sample data system requires the whole circuit and the whole circuit is going to convert the signal into analog form. So basically, I've already told you what is the meaning of sample data system. Sample data system is basically to have the whole circuit. Suppose input is a discrete signal, we are going to get like this. Suppose if I have discrete signal like this and I have given this signal to this basically what we can say for this sample to this sample data system, then output we are going to get like this. So it's just like we are going to get here. So in this fashion, so it is basically converting a digital signal to analog signal. So we can say sample data system is going to require the whole circuit and the whole circuit is going to convert the signal into the analog form. So we can say sample data system requires the whole circuit and the whole circuit is going to convert the digital signal into analog signal. Non-linear elements are sometimes intentionally introduced to improve the system stability. So we can say non-linear elements are sometimes intentionally introduced in order to improve the system stability. Sometimes in a given control system, sometimes non-linear elements are introduced intentionally to make the system stable. Sometimes we are going to intentionally introduce the non-linear elements in the control system in order to improve the stability. So we can say intentionally we are going to add the non-linear elements into the circuit in order to make the system to be stable. So therefore we can say that. So we can say that the non-linear elements are intentionally added into the control system in order to improve the stability. So we can say non-linear elements are intentionally added into the control system in order to improve the stability. So we can say intentionally we are going to add the non-linear elements into the control system in order to improve the stability. Non-linear elements are sometimes intentionally introduced in order to improve the system stability or improve the system stability. The next point is discrete data control system are susceptible to noise. So we can say discrete data control system are susceptible to noise means they can withstand the noise. They are capable of withstanding the noise. So we can say discrete data control systems are susceptible to noise, they can withstand the noise. Or we can say they can eliminate the noise also. So we can say discrete time control systems are susceptible to noise means we can say they can withstand the noise or they can control the noise, they can eliminate the noise. So this point always you have to keep in your mind. So discrete data control systems are susceptible to noise means they can withstand the noise. So these things always you have to keep in your mind. The next point is feedback can increase the system gain in one frequency range. So basically the feedback is going to increase the system gain in the one frequency range. I've already told you positive feedback. Positive feedback is going to increase the gain, whereas the negative feedback is going to decrease the gain. So feedback and also it is going to increase the system gain in one frequency range. So I already told you positive feedback is going to increase the gain, whereas the negative feedback is going to decrease the gain. So feedback can also increase system gain in only one frequency range. The next point is sensitivity considerations are important because physical properties may change with environment and aging. Sensitivity considerations are important because the physical properties may change with the environment and aging. Suppose I have taken some system. So as the time changes, as the environment changes, those element values are going to get changes. So because of this, the output is also going to get changes. So that is called as a sensitivity considerations. So sensitivity considerations are important because the physical properties may change with the environment as and the aging. So as time goes on, or because of the environment, the system parameters values are going to get changes. So therefore, there is effect in the output also because of this variation. So that is called as the sensitivity. So sensitivity considerations are very important because the physical properties may change with the environment as well as the aging. So therefore, we can say sensitivity considerations are very important because physical properties may change with the environment as well as the aging. So therefore, we can say the sensitivity considerations are very important because the physical properties may change with the environment as well as the aging. So therefore, we can say that the sensitivity considerations are very important because the physical properties may change with the environment as well as aging. So I already told you, as the environment as well as the age time goes on changes, the parameters of the system may going to get changes. So because of this, there is an effect in the output. So this is all about the sensitivity. The next point is gain margin is used for the study of the relative stability. So gain margin is basically used for the study of the relative stability. Suppose if I am going to construct two systems. For system 1, the gain margin is GM1, and for system 2, the gain margin is GM2. Suppose if GM1 is greater than GM2, then we can say the system 1 is more stable when compared to system 2. So more is the gain margin, more is the system stability. So by comparing two systems, gain margin we can say which is more stable when compared to other thing also. So gain margin is basically used for the study of the relative stability. The next point is the state transition matrix represents the free response of the system and also it is going to satisfy the homogeneous state equation. The state transition matrix represents the free response of the system and also it is going to satisfy the homogeneous state equation. And I have already told you what is the free response. Whenever the input is equal to 0, and we are going to get the output because of the state variables, that is or the initial condition, which is called as the free response. The state transition matrix represents the free response of the system and also it is going to satisfy the homogeneous state equation. So these things I have already told you so many number of times. Then this formula always you have to keep in your mind in the case of discrete time system. So in the case of discrete time system, if you want the initial value, f of 0 is equal limit z tends to infinity f of z is equal limit z tends to infinity, which is actually is 1 minus z to the power of minus 1 into f of z. So 1 by z is nothing but 1 by infinity is nothing but 0. So 1 by 0 is equal to 1 and f of z is f of z. Similarly, if you want the final value, f of infinity is equal limit z tends to 1 minus z to the power of minus 1 into f of z. So in the case of continuous time system, what is the initial value? In the continuous time system, the initial value f of 0 is equal to limit s tends to infinity s into f of s. Whereas the final value in the case of continuous time system is equal to limit s tends to 0 s into f of s. So this I already told you. But if you want to know in the terms of the discrete time system, then what we have to do? See, replace s by z. Replace s by z. So limit z tends to infinity. So here limit z tends to here 1. You have to keep here 1. Here you have to keep in place of s right here 1 minus z to the power of minus 1 into f of z. Here also same thing, 1 minus z to the power of minus 1 into f of z. So this formula always you have to keep in your mind. So here I am writing here basically in the terms of discrete time system, which is a limit z tends to infinity 1 minus z to the power of minus 1 into f of z. Here it is a limit z tends to 1 minus z to the power of minus 1 into f of z. So this is f of infinity. So we can see clearly an important point. Here this part is same, this part is same. Here also same thing. 1 minus z to the power of minus 1 to f of z, here also 1 minus z to the power of minus 1 to f of z. Here replace s by z, replace s by z, replace s by z, f by z. There is same infinity, but here replace 0 by 1. Remaining everything is same. So this formula always you have to keep in your mind. So this is for the discrete time system, and this is for the continuous time system. So initial value f of 0 is equal limit s tends to infinity s into f of s. The final value f of infinity is equal limit s tends to 0 s into f of s. But in the case of discrete time system, f of 0 is equal limit z tends to infinity 1 minus z to the power of minus 1 into f of z. In the case of the final value f of infinity is equal to limit z tends to 1 minus z to the power of minus 1 into f of z. So these formulas always you have to keep in your mind. So if you remember these formulas, you can easily solve this type of questions in a very fraction of seconds. So now the next point. So what is the next point here? This point now we are going to discuss in a very detailed manner. So we can see the right hand plane of the S plane when mapped into the Z plane covers the entire portion of the outside the unit circle. This one I already told you so many number of times. That is, the LHS of the S plane is mapped inside the unit circle in the Z plane, and the imaginary axis of S plane is mapped on the unit circle of Z plane, whereas the arches of the S plane is mapped to the outside the unit circle. So listen carefully. So we can say the LHS of the S plane is mapped inside the unit circle, and the imaginary axis of the S plane is mapped on the unit circle of Z plane, and the arches of the S plane is mapped to the outside the unit circle. So this point always you have to keep in your mind. So therefore finally I can say the LHS of the S plane is mapped inside the unit circle, and the imaginary axis is mapped on the unit circle, and the arches of the S plane is mapped outside the unit circle. The next point is, compared to continuous time systems, discrete time systems are more stable. So this one I already told you so many number of times. But now we are going to compare the continuous time system and discrete time system. The discrete time systems are very stable when compared to continuous time system. That is the reason always we prefer to use only the discrete time and discrete time systems only. So compared to continuous time system, the discrete time systems are more stable. Or we can say discrete time systems are more stable when compared to continuous time systems. The next point is, an example of a time varying system is rocket. See, whenever the rocket is going upward, the mass of the rocket is going to get vary as per the time. So we can say it is a time varying system because the mass of the rocket is going to vary as time goes on. So we can say it is said to be time varying system. The next point is, the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. So we can say the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. So we can say the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. So we can say the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. So these points always you have to keep in your mind. So therefore we can say that the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. So finally I can say the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. So finally I can say the methods to analyze the time varying systems are the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. So finally I can say the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. So finally I can say the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. So finally I can say the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. And the methods to analyze the LTI systems are the Lipinus method. So this one always you have to keep in the mind. So we can say the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. Whereas the method to analyze the LTI, or we can say linear systems, are the Lipinus method. So this one always you have to keep in your mind. So which method is used for which one, always you have to keep in your mind. Which is, we can say the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise linear method. Whereas the method to analyze the LTI systems are the Lipinus method. So finally I can say The methods to analyze the nonlinear systems are the phase-plane method, describing function method, and the piecewise linear method. Whereas the methods to analyze the LTI systems are the Lyapunov method. So this one always you have to keep in your mind. The next point is, so this point always you have to keep in your mind, which is in the case of digital systems. So in the case of digital systems, computer is basically used as the controller. So we can say in the case of digital systems, computer is used as a controller, whereas the A to D converter is used as the sampler, whereas the DDI converter is used as the hold. So basically, this we can see clearly, computer is basically used as a controller, A to D converter is used as a sampler, and the DDI converter is basically used as hold. So DDI converter means digital to analog signal, digital to analog signal. So if this is the digital input, then we need to get the analog signal with the help of hold. Hold means keep this one as it is for all the time, keep this one always like this one, keep as it is like this. So this is basically converting the digital, we can say DDI converter is basically converting digital signal to analog signal with the help of hold concept. So we can use it as a hold. So we can say in the case of digital systems, computer is basically used as controller because computer can give the control signals for the plant in order to make the output is equal to the desired output. Is the actual output always we have to get it is equal to desired output. That is the basic function of the computer. So whereas the AD converter means analog digital converter, it is basically used as a sampler. Sampler means we can say, see basically there is an analog signal. I want to get the digital signal. So with the help of sampling, at some particular time of instant, we are going to get the digital signals. This is called as a sampler or sampling. So with the help of sampling, we are going to get the digital signal from the analog signal. So therefore, we can say simply in the case of the digital systems, computer is basically used as the controller, whereas the analog to digital converter is used as the sampler, whereas the digital to analog converter is used as the hold. So this one always you have to keep in your mind. So we can say finally, in the case of digital systems, computer is used as the controller, whereas the analog to digital converter is used as the sampler, whereas the digital to analog converter is used as the hold. So this one always you have to keep in your mind. So therefore we can say finally, in the case of digital systems, so we can say finally, in the case of digital systems, computer is basically used as controller because computer is the only thing which can give the signals to the plant in order to make the output is always equal to the desired output. So because of this reason, we can say the computer is basically used as a controller, whereas the analog digital converter is used as a sampler, whereas the digital to analog converter is used as the hold. So finally, I can say in the case of digital systems, computer is used as the controller, whereas analog to digital converter is used as a sampler, and digital to analog converter is used as the hold. So this concept always you have to keep in your mind. So the next point is, if any one of the state variable is independent of the control U of t, the process is said to be completely uncontrollable. And then there is no way of driving this particular state variable to desired state in finite time by means of a control effort. I have already told you what is the meaning of controllable. Controllable means in order to control the state variables. Observable means in order to measure the state variables. So we can say if any one of the state variable is independent of the control input U of t, the process is said to be completely uncontrollable. And then there is no way of driving this particular state variable to a desired state in finite time by means of a control effort. So in simple words, I can say that even if any one of the state variable, if it is independent of the control input U of t, then the whole process is said to be completely uncontrollable. And there is no way of driving this particular state variable to a desired state in a finite time by means of a control effort. So finally, I can say that even if any one of the state variable is independent of the control input U of t, then the whole process is said to be completely uncontrollable. And there is no way of driving this particular state variable to a desired state in a finite time by means of a control effort. So in simple words, I can say, suppose even if any state variable, if it is not controllable, then the whole process is said to be uncontrollable. Similarly, even if any state variable, if it is not measurable, then the whole system is said to be, we can say this, not observable or unobservable. So these things I already told you. Even if any state variable, if it is not controllable, in the whole process called as the uncontrollable. Similarly, even if one state variable is not measurable, then the whole process is said to be unobservable. So this one I already told you. So therefore we can say if any one of the state variable is independent of the control input mu of t, then the whole process is said to be completely uncontrollable. And there is no way of driving this particular state variable to desired state in a finite time by means of a control effort. So finally I can say if any one of the state variable, if it is independent of the control input mu of t, then the whole process is said to be uncontrollable. And there is no way of driving this particular state variable to a desired state in a finite time by means of a control effort. So finally, I can say in simple words like this. See, even if one of the state variable is not controllable, the whole process called as the uncontrollable. Similarly, if one of the state variable is not measurable, then the whole process called as the unobservable. So therefore, we can say if any one of the state variable, if it is independent of the control input mu of t, then the whole process is said to be completely uncontrollable, and there is no way of driving this particular state variable to a desired state in a finite time by means of a control effort. The next point is the facts about the state model and the state equation is the state vector x of the system is not unique. The eigenvalues of A are the poles of the system transfer function. The minimum number of state variables required is equal to the number of independent energy storage elements in the system. So listen carefully. So now we are going to discuss some facts regarding the state model as well as the state equation. State equation means it is x dot is equal to ax plus b and y is equal to cx plus du. So each is called as a state equation and overall is called as a state model. The state vector x of the system is not unique. Means we can say the state vector means x. It is not a unique one. It is not a unique. Similarly, the state model is also not a unique. Whereas the eigenvalues of the matrix A are the poles of the system transfer function. So whatever the eigenvalues means, the determinant of SA minus A is equal to 0. So if we solve this one, we are going to get the eigenvalues of matrix A, which are called as the poles of the transfer function. Means we can say these are the closed loop poles of the transfer function. And the minimum number of state variables required is always equal to the number of independent energy storage elements in the system. I've already told you the order of the system is always equal to the number of energy storage elements present in the system. I've already told you the order of the system is always equal to the minimum number of energy storage elements is present in the system. So therefore, the minimum number of state variables is always equal to the number of independent energy storage elements in the system. Or simply we can say the order of the system is equal to number of independent storage elements, or we can say the minimum number of state variables also. All these are equal. So the order of the system is always equal to the number of energy storage elements as well as it is equal to number of state variables also. So these facts always you have to keep in your mind. So finally I can say some important facts regarding the state model as well as the state equation. State equation is z is equal to x plus du, y is equal to cx plus du. Individually both are individual statements are called state equation, but if you combine both it is called as the state model. So the state vector x of the system is not a unique. So whatever the x, it is not a unique. Similarly, the state model is also not a unique one. Plus eigenvalues of the matrix A, which are called as the closed loop poles of the transfer function, means the determinant of SA minus A equal to 0. If we solve this one, we are going to get the eigenvalues of the matrix A, which are basically the closed loop poles of the transfer function. And the minimum number of state variables which are required is always equal to the number of independent energy storage elements in the system. I already told you, which is the order of the system is always equal to the number of independent energy storage elements present in the system, or it is always equal to the minimum number of state variables. So this one always you have to keep in mind. So the next point is whenever we find the DC gain of the system, first arrange the transfer function in the time constant form and then substitute the S is equal to 0. So basically, if you want to find the DC gain of the system, first you have to do is the arrange the transfer function in the time constant form and then substitute S is equal to 0. You are going to get the result. So always remember, if you want to figure out the DC gain of the system, the first thing that we have to do is to arrange the transfer function in the time constant form and then substitute the S is equal to 0. So we can say that the first thing, if you want to figure out basically figure out the DC gain of the system, First, you have to arrange the transfer function, applying first and format, and then you have to substitute the s is equal to 0. So this will always be keep in your mind. So whenever, if you want to figure out the this gain of the system, first we have to arrange the transfer function, applying first and format, and then substitute the value s is equal to 0. So finally, I can say, suppose if you want to figure out the basic gain of the system, first we have to arrange the transfer function in the time constant format and then substitute the s is equal to 0. So the next statement is, the next point is, listen carefully. When we add a point to the infinite transfer function, then the root focus gets pulled to the right hand side. So then, so then what is going to happen? The stability is going to get decreases. Yes, the stability is going to get decreases. So because of this, what is going to happen? The steady state error decreases, the rise time increases, bandwidth decreases, system response gets slower. So what is the meaning of this one? I've already told you, adding 4 means simply we can say PI controller. PI controller means lag compensator. So in the case of lag compensator, what is the thing we are going to get? It is going to improve only the steady state response, but not the transient response. So it is going to improve the steady state response, but it is going to degrade the small amount of transient response also. So rise time is going to get increased, so bandwidth is going to get decreased because the product of the rise time and bandwidth is always equal to constant. So as the rise time increases, it will take a lot of time in order to get second. So the second time is also very, very high. So system response gets slow in order to reach the steady state value. It will take a lot of time in order to reach the steady state value. So finally, I can say, whenever we are going to add a point to the ultimate transfer function, the root focus is going to get pulled to the right hand side of the base plane. So because of this, the stability is going to get decreases. So it is nothing but it is a PI controller. Because of PI controller, we are going to get the pole. So then what is going to happen? PI controller means we can say lag compensator. Lag compensator is basically used to improve only the steady state response, but not the, it is going to deviate the small amount of transient response. As it is going to improve the steady state response, so therefore the steady state error decreases. So rise time is going to get increases. So bandwidth will decrease because the rise time bandwidth is always equal to constant. So system response is going to get slower because as the rise time increases, it will take a lot of time in order to get the second. So these things always you have to keep in your mind. Now the next point is, for a continuous time causal and stable LTI system, all the poles must have negative real parts and they must lie anywhere in the LHS of the S plane. But the zeros of the system can lie anywhere in the S plane. So listen carefully. For a continuous time causal and stable LTI system, so they are given a system which is a continuous time and the causal and stable LTI system, then what is the nature of the poles and the zeros we need to comment? Stable means definitely we can say all the poles must lie only in the LHS of S plane. They can lie anywhere in the LHS of S plane. But the zeros of the system can lie anywhere in the S plane. They can lie either anywhere, irrespective of the zeros. But definitely the poles should lie only in the LHS of S plane. So these points always you have to keep in mind. So for a continuous time, causal as well as stable LTI system, the poles must lie only in the LHS of S plane, and the zeros can lie anywhere in the S plane. So we can say, for a continuous time causal and stable LTI system, all poles must have negative parts and they can lie anywhere in the LHS of S plane, and zeros of the system can lie anywhere in the S plane. So finally I can say, for a continuous time causal as well as stable LTI systems, all the poles must lie anywhere in the LHS of the S plane, but all the zeros can lie anywhere in the S plane. So finally I can say, for a continuous time causal as well as stable LTI systems, all poles can lie only in the LHS of S plane, whereas the zeros can lie anywhere in the S plane. So the next point is, for 6 decibels per octave, it means that omega 2 is equal to 2 times of omega 1. And for 20 decibels per decade, it indicates that omega 2 is equal to 10 times of omega 1. So this one also I've already told you, which is plus or minus 6 decibels per octave is always equal to plus or minus 20 in decibels per decade. So this one I've already told you so many number of times. So plus or minus 6 decibels per octave is always equal to plus or minus 40 decibels per decade. So this formula always you have to keep in your mind, which is plus or minus 6 decibels per octave is always equal to plus or minus 20 n decibels per decade. So this formula always you have to keep in your mind. Therefore, we can say plus or minus 6 n decibels per octave is always equal to plus or minus 20 n decibels per decade. So what I told you, for 6 decibels per octave means omega 2 is equal to 2 times of omega 1. For 20 decibels per decade means omega 2 is equal to 10 times of omega 1. So this would always you have to keep in your mind. So therefore, we can say plus or minus 6 n decibels per octave is always equal to plus or minus 20 n decibels per decade. And for 6 decibels per octave, omega 2 is equal to 2 times of omega 1. And for 20 decibels per decade, which is omega 2 is equal to 10 times of omega 1. So this point always you have to keep in your mind. So therefore, we can say finally that plus or minus 6 n decibels per octave is always equal to plus or minus 20 n decibels per decade. And for 6 decibels per octave, omega 2 is equal to 2 times of omega 1. And for 20 decibels per decade, omega 2 is equal to 10 times of omega 1. So this formula always you have to keep in your mind. So finally, I can say that so plus or minus 6 n decibels per octave is always equal to plus or minus 20 n decibels per decade. And for 6 decibels per octave, we are going to get omega 2 is equal to 2 times of omega 1. And for 20 decibels per decade, we are going to get omega 2 is equal to 10 times of omega 1. The next point is the number of state variables of a system is equal to the number of integrators present in the system and the number of energy storage elements present in the system. As this point I told you so many number of times. See, in the case of state model, see whenever we are going to change the transfer function to state model, then I already told you the order system will never change. The order system is always equal to which is number of integrators present in the system or the number of energy storage elements present in the system. So this one I already told you so many number of times. Then the order system is always equal to number of state variables is equal to number of integrators present in the system or number of energy storage elements present in the system. So this one always you have to keep in your mind, which is the order system is always equal to number of state variables, which is equal to basically number of integrators present in the system or the number of energy storage elements present in the system. So finally, I can say that the order system is always equal to number of state variables or the number of integrators present in the system or the number of energy storage elements present in the system. So finally, I can say that the order system is always equal to number of state variables present in the system or the number of integrators present in the system or number of energy storage elements present in the system. So finally, I can say the number of state variables of a system is always equal to the number of elements present in the system and the number of energy storage elements present in the system, which is equal to order of the system. So you can write here it is equal to basically the order of the system. Order of the system. So let me write this point. So therefore we can say finally that the order system is always equal to number of state variables present in the system, which is equal to number of integrators present in the system or the number of energy storage elements present in the system. So finally I can say the number of state variables of a system is always equal to the number of integrators present in the system and also the number of energy storage elements present in the system or the order of the system. Anything just say. So finally, the next point is encirclement of origin of 1 plus g of s plane corresponds to encirclement of a point in the minus 1 plus g of s plane given by. Listen carefully, the question is encirclement of origin of 1 plus g of s plane corresponds to encirclement of a point in the minus 1 plus g of s plane given by. So let's solve this one. 1 plus g of s is equal to 0, equation 1. So adding minus 2 on both sides, then we are going to get 1 plus g of s minus 2 is equal to minus 2. So if we simplify, we are going to get minus 1 plus g of s is equal to minus 2. So this is the equation 2. So you can see clearly minus 1 plus g of s plane corresponds to minus 2 plus j0 point. So in the question what they are given, the encirclement of origin of 1 plus g of s plane corresponds to encirclement of a point in the minus 1 plus g of s plane given by. So basically what they are asking is very simple. See, suppose here I have taken one plane, here I have taken another plane. Here the plane is 1 plus g of s. Here the plane is minus 1 plus g of s. So here we are doing the encirclement at origin 0, 0. Then here, for this one, at which point we need to do the encirclement? So that is what we need to figure out. So you can see probability job is equal to 0. So add minus 2 on both sides, and we are going to get finally minus 1 plus job is equal to minus 2. So minus 2 means we can write minus 2 comma j0 or minus 2 plus j0. So this is the point here. So the point is minus 2 comma 0. So this is the point. At this point we are going to do the encirclement. So here at 0, 0 we are going to do encirclement. Here at minus 1, 2, 0 we are going to do encirclement. So this point always you have to keep in mind. So here they are given 2 planes. One plane is of 1 plus g of s and the other plane is of minus 1 plus g of s. So for the 1 plus g of s plane, we are doing the encirclement at origin. Then for minus 1 plus g of s plane, at which point we need to do the encirclement, we need to figure out. So here, this point is basically we are doing the encirclement at origin is equal to 0. So 1 plus g of s is equal to 0. So this is the equation 1. So for this equation, if you add minus 2 on both sides, we are going to get finally minus 1 plus g of s is equal to minus 2. So for this one, we are doing encirclement at minus 2 comma 0. So this is the point always you have to keep in your mind. The next point is, so this is a signal flow graph they are given. R is the input and C is the output. So we have to find the number of forward paths. Number of forward paths means always you have to travel from input to output along the arrows, not traveling any node more than once. So therefore we can say, so this is a one forward path and this is the another forward path and this is the another forward path. So total we have 3 forward paths. So we can say this is the one forward path, this is the other forward path and this is the third forward path. So total we have 3 forward paths only. So we have only 3 forward paths. The number of loops you can see clearly. So this is the one loop here. So you can see this is the one loop. So you can see this is the one loop. And the next loop. So what is the next loop here? So this you can see this is the another loop. So this is the another loop. So you can see this is the another loop. So listen carefully. So this is the another loop. Okay. Then finally, what is the another loop? Finally. So now one more loop is, if you see clearly, you can even see the other loop also. So what is that loop here? Listen carefully. So this is the another loop. So this is the other loop. So we have 3 loops. So this is the first loop, this is the second loop, and this is the third loop. So this point you can see clearly here. So total we have 3 loops. So loop 1, loop 2, and loop 3. So for the signal flow diagram we have 3 forward paths and 3 loops. Forward path means always you have travel from input to input point to the output point by traveling along the direction of the arrows, but not traveling any more than once. Closed loop means the initial point is equal to final point, and without traveling any more than once, always you have to travel in the direction of the arrows. So these things always you have to keep in your mind.